Hey, Axel.
Hey, how you doing?
Good. Everything for the workshop been running smooth on your end?
Oh, yes. A few little hiccups, but I don't think you've noticed them.
Yeah, I don't think I have. So Fernando is helping out this morning with the parallel Zoom calls.
I hope so.
Okay.
When his little daughter lets him away. Nah, I'm joking. I mean, he's a very dependable and reliable colleague.
Good. I'm gonna grab my little stopwatch. Axel, in my first talk, if I get like 2 minutes to the end, maybe just chime in because my first talk might be a little long. I'm going to try to shorten it as I go, but I don't want to overshoot. My second talk I don't think will be too long, so there's not a worry.
Yeah, I don't know. I don't have that much either. I'll let you know.
Great. I'm going to try to share my screen. Is that full screen now?
Yes, it is.
Okay. You want to go back to your logo until I can put this up a couple minutes before we start?
It's up to you, just like you. Okay, let me just. You notice I got the fancy clock back.
Oh yeah.
I had to actually port it. It was written like more than 10 years ago, and Fedora stopped supporting it with the last edition because it was unmaintained.
Okay, I'll put up my slide, Axel. For people who are already on the Zoom call, we're planning to start the session at 5 till the hour, so we have a few minutes still. Thanks. Hey, Axel, I just thought of something. When we have parallel breakout sessions and there's speakers logging in with the panelist link, is that the same link for all the breakouts, or are there like two panelist links when they're parallel?
People have been sent the link for the second session only, the panelist link only for those who are actually panelists.
Oh, okay, so those emails were tailored for everybody to get the right one, in other words?
Well, I had to take the list of those speakers and give it to my colleague who runs the parallel Zoom session.
Gotcha, great. Okay, I think we're at 5 till the hour. Should we start? Are we ready to go, Axel?
I'm as ready as ever.
Okay. All right. Well, welcome everybody that's joined for the last day of the LAMMPS Workshop and Symposium. Today, the first hour is still for everyone. It's a developer session and aimed at people who not only want to use LAMMPS, but might be interested in writing code for new features or extending the code to do new kinds of things. So that's our focus for this hour. Following this hour, the second hour of the first session will be 2 parallel breakouts with contributed talks. And then the later session, again, 2 hours as usual, will have, I think, actually 5 breakouts. There's 2 parallel the first hour and 3 parallel the second hour. And you should have gotten Zoom links to all of those from Stan, both by email, and it's in the Slack channel if you didn't see that. And so you can use those. You have to use different Zoom links, obviously, for different parallel sessions. And so you should look at that and see which ones you want to attend. So for questions all during the day, including at the end of this developer session, you should use the Slack channel. And I think we're just all going to use the general Slack channel, both for this one and the breakouts. And hopefully it'll sort itself out. People can figure out which question goes to which talk. You can put the speaker's name in it if you like, so that it's easy for us to scan and try to address those questions. Okay, so this is the schedule that's posted here for our 1 hour. We're going to have 3 short talks by myself and Axel, about 15 minutes each, and then we hope to leave 15 minutes at the end for kind of a group discussion, Q&A. And so throughout the session, you can post talks or post questions either about these 3 talks or other more general LAMMPS development questions that you might have, and then we'll see how many we can get to, and Axel and I can try to answer those together. Okay, so I'm going to flip to my talk here in just a second. The slides for my 2 talks are actually on the workshop website, day 4 for the development session. And so if you want to download those PDFs and watch it that way or look at them that way, that's fine. Okay, let me try to get out of. Oh, I think I'm going to have to stop sharing for a moment and flip my slides to a different talk. Okay, full screen on how to modify LAMMPS. Is that working, Axel?
Yeah, looks good.
Okay. All right. So this first talk is about how to modify and extend LAMMPS, leading towards the idea that you're maybe going to write some code for LAMMPS itself. And I'm going to talk about this in 6 stages. I have a couple slides on each of these topics. So I'll go through these questions one by one. But they're ones for you to think about, and in particular, the first 4 answers to the first 4 questions might convince you don't actually need the idea or feature you have in mind in LAMMPS itself. You might be able to do it alternate ways that would maybe be a little simpler. All right, so let's start with the first question, and that is, does LAMMPS already have a similar feature to what you want? And the reason that's important is if it is, or if there is, maybe it's sufficient for what you need. Maybe it can be incrementally extended instead of starting from scratch. And maybe its code will show you how to implement your feature, which might be somewhat different. So this is the best way to figure that out. Check the LAMMPS website and manual. The website, a little ways down the main page, has a Google search bar that limits the search to the website, which includes the manual. There's also at the top in the little table of links a glossary link, which will take, you can look for an MD terminology, an algorithm or a kind of modeling, and it will map you to some LAMMPS commands that might do what you want. And then the website has a commands link, again, in that little table at the top, which we talked a lot about during the tutorial. It actually takes you inside the manual to a set of alphabetized tables for pair styles, fixes, computes, etc. And then on the fix command doc page itself, there's a 1-line description of every fix, a couple hundred of those, likewise for computes and pair styles. So scanning through those might find you information about what you're looking for. And then whenever you're in the manual on the LAMMPS website, every manual web page at the upper left corner has a little search docs bubble. And so you can type in there and limit your search to within the manual. And again, looking for some text that might be related to the feature or option that you're interested in. And then Google's obviously very powerful. Now it even thinks for us with AI. You can type prefix whatever you're looking for with LAMMPS, and you'll often find useful stuff, not just within the website, but within the MatSci forum, which includes old mail list posts and just other people who've done stuff with LAMMPS or talked about LAMMPS. You might find some useful hits on what you're looking for. Okay, second, have others discussed or worked on this idea before? So there's 2 places to look for that. One is the MatSci forum, and that's a umbrella site for many materials modeling codes. LAMMPS is just one of them, but LAMMPS has its own forum on that site. And the top of the LAMMPS webpage, the very upper left of that table, there's a link to MatSci forum, which gives you some information about it, how to join, how to browse it, that kind of thing. And so you can look through the postings there. On the LAMMPS GitHub page, there's an issues portion. That's the link to the LAMMPS. I'll see if my mouse works here, to the LAMMPS GitHub page. You can look through the issues, but that includes bug reports and other things. The best place, I think, is to look at the projects link at the top of the GitHub page. and then click on LAMMPS feature requests, and that will list the subset of issues that are actually about new features. And so you might see your idea in there. And if nothing shows up there, you can use the MatSci forum to ask a question about your new feature. It's good to give a big picture of what you're trying to do, because it may be already possible in ways you're not thinking about, that the big picture will let other people answer and give you some ideas. Okay, third question. If you haven't found it elsewhere and you're going to need to do this, is it better to implement the feature you want outside of LAMMPS or actually inside LAMMPS? Well, here's some ideas that make the answer maybe better to do it outside. So one would be pre or post processing tasks, and you can look on the website, again, that little table at the top, there's a pre-post processing link that points at many different tools that work compatibly with LAMMPS. Another idea is if it's a complex operation you want to do and it's only kind of loosely coupled to LAMMPS. So I'll give 3 examples of that. So one would be there's another program that you want to kind of interoperate with LAMMPS and its input script. So that could be an existing program that already does something nice, or it could be a new program you plan to write, a Python script or in some other language. Well, there's a shell command in the LAMMPS input script that can invoke a program with arguments, either of these kind of programs. And then the results, the program could write its results to a file. Maybe it's a number or a few numbers. Input script variables can read numbers like that from a file. And then you've got a variable in a LAMMPS input script that can influence LAMP commands. Or the program could exchange data with LAMMPS by files that LAMMPS knows how to read and write. Another mode of coupling 2 codes together, LAMMPS and another code, is what's called client-server coupling. And this is best typically if the data volume that needs to be exchanged between them is relatively modest, and maybe a single processor in each code can do the task of getting that data. So let's imagine 2 independent codes and use a quantum code, QM, as an example. So if you want to couple QM with LAMMPS, that enables you to do ab initio MD or QMMM style coupling. And LAMMPS actually already has support for this intercode coupling through client-server models with a package called MDI, and it's a wrapper on an MDI library that's provided by the MALSI project. And so it's especially tuned for coupling atomistic codes to quantum codes, but actually it's a general coupling language. You could adapt it very easily in LAMMPS to couple to other kinds of codes. And so what you have to do is have the other code also have some MDI support. If you own the code, it's not hard to add it, but you can also wrap an existing code, even kind of a black box code, with Python and have the Python part provide the MDI support. So then you can run the 2 codes together on different sets of processors in parallel, or even have one load the other as a plugin. So see this section in a how-to, it's called How to MDI in the manual for more information about this kind of coupling. And finally, if the other code is actually a library, then you could wrap that external library with a new LAMMPS style, which the style itself doesn't necessarily have to be very heavyweight. That's much simpler than writing all the functionality in the other code. This is often best if the data volume is large, because if the library is parallel like LAMMPS, then you can do a parallel exchange of data through the library API. So 2 examples of this in LAMMPS: the compute Voronoi/atom command wraps the Voro++ library, which does nice Voronoi tessellations, in this case around atoms as points and getting the closest volume around every atom. The peristyle Kim command, which was talked about a little bit in the tutorial, and there's a breakout on that today, the whole OpenKim infrastructure. That peristyle command is really a wrapper on the OpenKim library, which has a huge archive of different interatomic potentials. And so it makes calls to this library to trigger LAMMPS to run a simulation with one of those potentials. Okay, so here's some cases where the idea you have is probably better done inside LAMMPS. 3 things to think about. The first is if the new feature needs to be invoked frequently during time stepping. That would be the case for something which is like a peristyle, a fix, or a compute. And it's also maybe going to be a bottleneck if it's not implemented in parallel, in which case you need to think how to make that operation parallel, similar to the way LAMMPS operates in parallel. And finally, if you think it needs to be coded in C++ for speed and not wouldn't be sufficient maybe in some of those other modes I just talked about. Okay, so if you are going to do it, let's come back to that speed issue. Is a question to ask is, even if it's going to be done in LAMMPS, can it be done with Python instead of C++? Motivations for that, obviously, it's often quicker to try something out and debug it in Python, and it may turn out Python is fast enough. You don't really need to write C++ code for what you're implementing. And Python certainly can run in parallel via its MPI for Pi module, just like LAMMPS. And so each LAMMPS processor could be talking to Python, and both your new thing and LAMMPS itself would be running in parallel. So there's many, many ways to use Python with LAMMPS. I'm just going to highlight a few here which are relevant to this idea of adding new functionality. You should see section 2 of the programmer's guide, which kind of has details about all of these. You can have your Python script wrap LAMMPS and use it as a library, and then it can invoke input script commands. It can query and set internal data. So you might be writing your functionality, your new functionality in this wrapper and just operating with LAMMPS as a library. And there's really 3 interfaces for that in Python: lamps.py, which is provided, all of these are provided in the distribution. Lamps.py is a kind of direct C style wrapping on the library. PyLamps is a more Python flavored wrapper on that interface. And then IPyLamps is an extension of this that adds Jupyter notebooks if you want to do interactive kind of development and presentations. And then Python, or LAMMPS itself, has a fixed internal command which can, during a time step, call back to a driving code, in this case, say a Python driver. So you can, within the middle of your time step, call back to your Python driver where you've written a function, and that function is going to influence the LAMMPS time stepping. There's also, in the input script, Python style variables, and they can invoke a Python function directly. So now you're not using it Python to wrap the LAMMPS interface. You're just triggering Python from within LAMMPS itself. And that Python function can still call back to LAMMPS, access its internal data, and return something, a value or two that's going to be in this Python variable for the input script to use. And then there are, in fact, fixed Python and pair-style Python commands, where the different methods in there for operating at different parts of the fix or triggering pairwise interactions, those can be written in Python and used directly in LAMMPS with these styles. And so I'll note that 2 years ago at the 2021 workshop, Richard Berger gave a 30-minute talk about different ways to use Python with LAMMPS, which is still relevant. You could watch that talk. And Jan Janssen today is giving a 1-hour breakout later on his tool, a Python-based framework that's very nice, Pyron, which will show you how writing stuff in Python and then using LAMMPS as an MD engine in this case, you can do lots of interesting materials modeling kinds of tasks. Okay, so now you're to the point, I think this might be my 5th stage of the questions on the first slide. Decided you really need to add some C++ code to LAMMPS. Well, the first step, please take a look at the programmer guide. Axel in particular has put a lot of work into it over the last 2 or 3 years. It's being continuously improved, new content added, but maybe there's something you think we've missed that would be useful, and you can talk to us and we can maybe add some information about that for from a developer's point of view. I want to point you in particular to section 4, information for developers in the programmer guide. It explains the LAMMPS class hierarchy, how a time step works, how communication is done between processors, lots of useful utility functions and classes, which the code you write can leverage, and then some low-level descriptions of LAMMPS internals, like the base classes, neighbor lists, the tokenizer class, which is very good if you're going to read in a file with information that is used by a pair style, for example. And then a new section, which I'm actually going to talk a little about in the 3rd talk today, about distributed grids and FFTs. Okay, so now you're to the point you're going to write new code. It's probably going to be a new style within LAMMPS. And in LAMMPS lingo, a style is a child class derived from a parent class. And really, I say you're probably going to do this because more than 90% of the LAMMPS code base is added styles, either by developers or users that have wanted to extend LAMMPS with a particular functionality. So section 3 of the programmer's guide is all about modifying and extending LAMMPS through these style classes. And so there's, with a slant on people who are writing code, there's these kind of descriptions of all the common styles, including these 4 I've listed here. I'm not going to talk about them in detail, but you can see different sections in that part of the programmer's guide. And then in section 4, there's some concrete examples for writing new styles that are written kind of in a tutorial fashion. So these are step-by-step instructions with code snippets. And again, Axel is the one that's created this nice new content. And so it sort of steps you through a step at a time how you start with a blank pair style or a blank fixed style and how you add functionality to have it do what you want. So for the pair style case, there's 4 examples, and including not just a simple pairwise interaction style, but a mini body potential and 1 example of a fixed style. So that's a good place to start as well if you want a gentle introduction. Okay, so do you think you're going to need some help implementing the new feature? Well, the best thing to do first is find a similar style already in LAMMPS. That can show you which methods you need to define, how to make calls to other LAMMPS functionality. And so some examples of that here, you could look for a fix that operates at the same point in the time step that yours does. A computer fix that needs a neighbor list, there's many of those, and you could see how that's done. Or ones that produce the same flavor of output data so that other commands can grab that data. Or fixes that persist per atom data across time step, that requires you to implement a few methods. Or fixes, pair styles, or computes that require communication. That's done in a particular way in all those cases. You can always ask the LAMMPS developers for advice. If these other steps don't get you where you need to be, you can do that via the MatSci forum or create a GitHub issue like I talked about before. 2 reasons to not just directly email the developer, at least as a first idea. One is that others can answer if you do it in these more public ways. And then the question and answer is archived, so others might learn from it in the future. But if all that fails, you can certainly send an email to developers@lamps.org and we'll take a look and try to give you some feedback. Okay, just a slide or 2 left. One final question: is the feature you're implementing, is it just for you and your research group to use, or you want to actually eventually release it in public LAMPS? Well, if it's just you, obviously you can implement the feature in your style classes however you want. You can even create an external package if you have several related styles, and then distribute it from your own website or your own GitHub page. And we can advertise your code for you. Look at if you tell us about it, look at the external packages link on the website and you'll see several of these kind of packages that other people have created, and we just point them to do, and you give people instructions on how to integrate it into LAMMPS and build and run your model. So if you're intending it for eventually to go in public LAMMPS, then follow the guidelines on the next slide, which is my last slide. But first, I'll just give you a bit of motivation about why you might want to contribute your code to public LAMMPS. It's certainly been our kind of open source philosophy to have a user community that shares things and helps each other do new kinds of simulations. I say fame and fortune here in red, kind of satirically, but your name will be on the website, author page, and in the source code. And if you have a paper about what you've done and how LAMMPS implement it, you can have LAMMPS output a citation when someone uses your feature. And then, of course, people who use it may find and fix bugs, extend its functionality, may even become your collaborators on using that new idea on different kinds of simulations. So the last slide, here's the quick rules of thumb for contributing code to LAMMPS. All of that is done through GitHub. So you should familiarize yourself with that site. Read Submitting New Features for Inclusion in LAMMPS in the Programmer Guide, a subsection that gives you some kind of a checklist of things to think about before you submit a pull request. The coding style of what you write in a 1-line nutshell, we want new code that looks like existing LAMMPS code. So you should try to follow that as best you can. And then finally, for any new command you have that's a new style, you're going to need a doc page in the RST format. You can look at those text-based files in doc/source. If it's a new model, you might want to provide a new examples folder that has input scripts to test it. If at all possible, limit your changes to these new style files you're creating. If there's some non-trivial change to a LAMMPS core file you really think is needed, then ask the developers so we can talk about that with you. And if you're unsure what's the LAMMPS way to do something, always helpful to ask in advance. That helps you avoid being asked to maybe rewrite your code after you submit some part of your code after you submit a pull request. And I think with that, I will stop. Hopefully I kept close to my time. Okay, so again, we won't take questions now, but we will at the end. So put anything you have in the Slack channel, and I'm going to unshare and let Axel do the second talk.
Okay, so yeah, Steve, you had perfect timing. So I want to talk a little bit about a few things that have happened in the development process in the last couple of years. So there's a more detailed talk from me in the workshop 2 years ago, because ultimately, so we're trying to update LAMMPS so it can be remain relevant, and it's getting easier to maintain and easier to contribute to it. So I'll just focus on the things that have changed in the last couple of years. Most of the stuff we started basically with the beginning of the pandemic, when we were scooped out at home and had the time to do things that went beyond just regular keep on going, are still ongoing, but so it's less visible. It's just incremental changes. So we're still working on improvements to the programmer's guide. There is multiple different details of source code refactoring, specifically with respect to error messages. There's continuous improvements to the CMake build system. We're fine-tuning our GitHub workflow and some of the rules. You may have seen that there is these projects entry that is a new thing that has a like Trello style presentation of open pull requests and issues that allows you to see how we categorize and prioritize ongoing feature requests, bug reports, and pull requests. We're expanding still automated testing and static code analysis. We want LAMMPS to be more reliable, and we don't want old bugs to come back. So that's one of the reasons why it may actually be more difficult now and more laborious to contribute to LAMMPS, because we have improved the quality of the overall quality of the code, and we want to keep it like that. And as you know, this is like keeping bugs out of your house. You have to be vigilant and keep going. And there's small tweaks to the release management tool. So let's get into the details. So in the programmer's guide, there are more and refined explanations to the code design, also aimed at people who are not necessarily big C++ experts, but the C++ part is becoming more relevant. LAMMPS source code becomes more C++-ish, because many of the features in modern C++ make code maintenance easier and allow it to do the same thing with far fewer lines of code. There's a new section about how to access paradigm data and what is there. Steve already mentioned communication patterns and the step-by-step guides to write styles. I have to correct him. The fixed style guide was contributed many years back. That was not mine, but nevertheless, it has been revised. We added, and that seems to be really important now, we added notes on porting old code to current LAMMPS. There seems to be quite a bit of fixes and pair styles around that people keep using, but the original authors are not updating them. And we've actually created a repository, LAMMPS packages, where we can help to at least make them so they compile with current LAMMPS. Many times those don't make the requirements for merging into LAMMPS because, for example, there's no documentation, or the implementation may not be complete or may be limited. There's one exception to the rule. The SGCMC fix was recently updated by Aidan and me, and that is now moved from first being in the packages repository and updated to compile and to be usable. And now it's actually part of the LAMMPS distribution. So if you want your stuff to get be merged, this is another avenue that you can have it added to the LAMMPS packages repository, and we help to port it, and then you can keep working on it. while before it is actually in LAMMPS, and people, you can still share it and people can see it. Okay, another feature that was added is abstraction convenience functions for platform-specific tasks. That has helped us massively to improve portability. So we're really portable to Windows now, or with both the Visual C++ and the GCC compilers, macOS. There were some glitches that popped up every once in a while. This is also a thing of the past now. Steve will talk about the distributed grid. So there's information in the programmer's guide. And overall, we've had a few volunteers that went through the entire many thousands of pages and tried to make everything more consistent and work with the theme that Sphinx applies. So I mentioned the platform abstraction. We have removed some packages because their functionality is obsolete. So the message package and Latte were removed because that's now handled by MDI. And MSCG is now a standalone re-implementation in Python, so that one's not needed anymore. With the help of Carl Hammond from University of Missouri, if I remember correctly, we have now a complete Fortran module, and we've ditched the old unmaintained ones. So this is now a wrapper that wraps all available library functions. There's a way to do the Fortran library, the C library access by loading the shared LAMMPS library as a plugin at runtime. That has also been tested and completed. A very recent change is there's a few dump styles that were accessing thermodynamic data during the run and output it in the dump. Most dumps are per atom or local data. And to do this in a clean fashion, we're caching thermo data. And this is also accessible via the library interface. And I'm also taking advantage of that to make plots in the LAMMPS GUI. So it can be used very conveniently to introspect what is happening in a given LAMMPS instance. And for that purpose, overall, there's more utility and introspection functions, so you can check which features are compiled into the specific library and make your code adapt to whether this is available or not. Like if you can use multi-threading or GPU acceleration, you can detect this. We've revised how you request neighbor lists. There is far fewer code needed, and you don't have to modify a struct. You just request and give flags what you need, or call a function that says change this property, and it's done consistently. Previously, you could easily make that inconsistent and have very bad behavior. And we're ongoing to work and improving error messages. Basically, in the past, the strategy was LAMMPS prints a message says there was an error, and it was giving the 9 number of the source code. And then you would look up in a list of error messages whether there is some additional information about it. Now we're putting it right in there, and we're kind of dropping those extra lists. And you don't have to look, hopefully, at the source code to figure out what exactly is happening. But that has happened only to a small part of the code, so we're looking for volunteers to help with that. Changes to the build system. So we revised the make install Python process. It was using some deprecated feature set in from the Python distribution. So now when you do this, there's a virtual environment created in which a wheel is produced, and this wheel file is like a package with the binary and the Python code bundled, and that can then be added to your local installation via pip. So in make install Python does these 2 steps in one go and tries to install it. And then it can also, if you basically, it can update the package, because the wheel package you can uninstall completely. What we did previously, you had to manually delete the files. So if you did this before, you have to at least once delete everything, but from then on it's pip uninstall and the LAMMPS Python module is gone, and then you can just keep a copy of the wheel file and can install it again. Same for virtual environments, etc. One thing where the CMake version was lacking compared to the traditional Make version is if you just copy some files over, you would explicitly have to rerun CMake to make it take note of these files. This is now automatic. It requires a newer version of CMake, but that's actually not going to be an issue because with the current development version, we're now requiring CMake version 3.16, which corresponds to Ubuntu 20.04. Overall, bumping up the CMake requirement makes it much easier and more reliable. And we can use more advanced features of CMake to make the build procedure more seamless and automatic. The CMake specifically has been upgraded so that it can build almost anything on Windows. We have nearly complete support for most of LAMMPS from within Visual Studio now. And so there is almost no need to use the Windows subsystem for Linux if you want a full-fledged LAMMPS executable. And I would say the way it's been set up, if you want to program from an IDE, the Windows Visual Studio experience is probably the most integrated and most seamless procedure to get started. But that's just how Visual Studio itself is built. But we're complete in terms of how to support it. There's just a few packages that need external source code that hasn't been adapted to be built from within on Windows, that just requires Unix environment or has some details that are not compatible. And another step is, so in the development branch, we've upgraded Cocos to version 4, which will require C++ 17. So in the Ubuntu family, that's effectively also minimum Ubuntu 20 instead of previously 18. And for other, you probably have to load some extra module for the compiler. Testing, similar thing, the test environment has been upgraded because we need to be able to handle CMake 3.16. We have tests on macOS and Windows Server run through GitHub, so not on Temple machines, and we're running automatic regular static code analysis with CodeQL on GitHub and Coverity Scan through the Temple setup. Oh, no, Coverity Scan is also on GitHub now. So that will often give us hints to newly added code that has weaknesses or little details that can be improved. Testing of the pair styles has been expanded to use Cocos OpenMP. Unfortunately, GPUs is still lacking some internal setup that we can detect what is possible to test. That's currently not yet done for Cocos. So, but it has helped to find some issues in the implementation already. So that is a good thing. We have more checks for coding style issues, and there's a simple, because it's so many, there's now a simple make check. If you go to the source folder, and it will check everything, and it will also list tags. So we're putting in the documentation tags. This is new in version so and so, and this was changed in version so and so, because we noticed that many people read the online documentation but are still using older versions of LAMMPS. And then they're assuming that what's written in the documentation still applies to them. And if we put these tags in the documentation, you can see that now you need to update to a more recent version of LAMMPS to use that feature. And there's a target to run Clang tidy. So we use that to detect some simple things that need to be updated. Overall, we're now maintaining 4 branches: develop, release, maintenance, and stable. Feature releases after about 500 commits, that's every 4 to 6 weeks, that will be moved from develop to release. Stable releases are about once a year right now. Those will then be moved to stable. we're releasing updates with bug fixes to the stable branch. Those will be handled on the maintenance branch. Ongoing development will merge to develop. And so the release branch is actually always fast forward merges from develop. So it's just resetting to a specific point in develop. Because of the updates, we can't do this with the stable branch anymore. So there's occasionally commits that have no other purpose than syncing stable with the develop branch. And there's excessive tagging, so you can get a tag for every release and branch. So this is basically a repetition, so I don't need to do this because I'm out of time. So the final point I want to make is we need you. So LAMMPS goes back nearly 30 years. And we hope that we can keep this going for quite a while. And we hope that you want to keep it going too. But as Aidan has mentioned, Steve has retired from Sandia. He's still around for LAMMPS, but nevertheless, and there's a few more within the core developers that have to look at retirement within the next, say, 10 years. So we need people that join the team, that grow into being able to do these tasks. And overall, with the growth of LAMMPS, we have just too many tasks on too few people. So we've grown the team a little bit with a few people specializing on a few things, but ultimately we need more, and this takes time. So people need to learn from us how we want to do things, how we have learned how to improve LAMMPS and to stick to a consistent approach and philosophy. And there just has to be some trust among all the people that make the decisions. So if you're interested to join, you just need to have some motivation, and you need to ask where to help, and we can give you some pointers and you can slowly make your way into it. That's how it happened for me. And we may be doing another event specifically for developers next year, and that might be a good point to start and learn more about what happens in LAMMPS development. And I think I should stop now.
Great, thanks, Axel. I didn't know you were going to make a plug in that last slide. I'm glad you did.
Oh, I warned you about it.
Okay, let me bring up my last set of slides. Okay, see the full screen?
Yeah, it looks good.
Okay. All right. So as I mentioned, I'm going to talk briefly, another 15-minute talk. I'm aiming to end by 8:45. See if I can make this quick. Hold on a minute. Let me get my little timer started. So this is about relatively new support within the last year that we've added to LAMMPS for distributed grids. And I'll first motivate that. LAMMPS obviously is a particle code, but using a grid or a mesh can be useful in several contexts. One is just analysis. You want to group particles and their properties onto a grid, which is a data reduction, maybe a much fewer grid cells than 1 billion particles. You can also do visualization on the grid cells, color each grid cell with properties. And then in the model sense, there's lots of different particle/grid models that need both capabilities to do their operations. So just 3 examples of those. Long-range coulombics, something LAMMPS has done for a long time. The motivation there for a method like particle mesh ewald is that FFTs are much more efficient than having a huge pairwise cutoff to do the long-range part of K-space interactions. So the idea is charge is mapped onto grid cells. Poisson's equation is then used on the grid to solve it via FFTs, and electric field values on the grid are mapped back to individual particles. So there's also a 2-temperature model that's in LAMMPS where you have your normal atoms, but you also store electron temperature on a grid. And so you don't model the electrons explicitly, but their temperature and the heat that they transfer couples back to the atom. So the heat equation is solved on the grid to do diffusion, and then that heat is coupled back to atomic motion. And then there's a variety of coarse grain models. One good example is the material point method, which is not implemented in LAMMPS, but potentially could be with this new feature. And that's a mesh-free, continuum-based material model. The grid is used to compute deformation gradients, and effectively advect grid points in a velocity acceleration sense, but that those values are mapped back to the particles to affect their motion. Okay, so what do we mean by grids in LAMMPS? Well, it's really a regular grid that overlays the entire simulation domain. So it can be a 2D grid or a 3D grid, depending on the dimensionality. And so at the left on the bottom here, here's an orthogonal simulation box, and I've just shown a bunch of particles in a 4x4 grid in 2D that overlays that domain. We can do the same thing for triclinic. So the box is tilted here, and the same 4x4 grid, each grid cell now is the same shape as the overall simulation box. The grids can be periodic or non-periodic, just like the simulation box, and the grids themselves can be any size in each dimension. So this was 4x4 in 2D, but it could be 1,000 cubed in 3D or different grid sizes in each dimension. You can even shrink dimensions, have 10 by 10 by 1, so that in the Z direction, there's just a single grid cell, or even down to 1 by 1 by 1, which would be a single grid cell for the entire simulation box. So that's probably not that useful. So what do we mean by a distributed grid? So the idea is each processor is only going to own grid cells whose center points are inside that processor's subdomain. So because the subdomains are rectangular or tilted rectangles in the case of trilinic, that's also always a subblock of the full grid. So you can also choose to have a processor store nearby ghost grid cells that your particles might interact with. And then this idea works with either brick or tiled spatial decompositions. So here's two little snapshots from the very initial snapshot and the final snapshot of a movie I'm going to show you in a couple minutes. And this is running on, these are the full simulation domains. These are the processor decompositions with these yellow lines. And what I'm showing here is not the actual particles like I'll show you in the movie, but I'm showing you just the grid cells that are assigned to each processor. And so you can see each processor owns the subset of grid cells that are within that processor. And it overlaps a little because the center point might be in this processor, but the extent of the grid cell goes outside that processor. And so this is an example of a tiled decomposition that would come from load balancing for an orthogonal box. And so in a normal situation, the grid cells are typically smaller than processor subdomains, but they don't have to be. As I mentioned, you can have a grid that only has one grid cell in the Z dimension, and so you might have multiple processors stacked up, but they would all be shared by processors in that direction. Okay, so now let's get into some coding details. What's been added to LAMMPS is a new grid 2D and 3D class for both 2D models and 3D models. They can be instantiated by any pair, fixed, compute, or K-space style. And what the class really stores is the partitioning of the grid across processors, not the data itself that's stored on the grid. See, I'm realizing maybe I forgot to turn on my camera. Sorry, if anybody's trying to watch me. I realize I'm motioning with my hands and you're probably not seeing that. Maybe that'll be helpful, maybe it'll be distracting. Okay, so again, the grid classes don't store data, they just store the partitioning. Oops, let me get to the next slide here. There we go. But the calling style can define multiple grids, say each one of different size, and it can define and store one or more scalar or vector data sets that live in each grid cell. So each grid and data field is named by the caller, and that means other commands in LAMMPS can access the data. So I should say what I mean by vector, if you have a single value for each grid cell, that's a scalar, but you might have an electric field vector per grid cell, that would be a 3-length vector that the grid stores or is mapped to the grid cells. So here's what a grid data reference looks like from another command. This would be a fix with a particular ID, and then a grid name and a data name separated by columns. And if it was a vector, this would be accessing the Z component of that vector for that grid set or that data set. So there's also support for forward and reverse communication. And just like for particles, forward means communication of own cell data to ghost cell data on other processors. Reverse is when you communicate and typically some ghost cell data from various processors back to the owning grid cell. And just like with particles, the caller will then provide pack and unpack methods that get called by the grid classes in order to chunk up the data and be able to send it to other processors. Similarly, for load balancing, if you completely remap which processor owns which subdomain, it also has to pick up a set of new grid cells and the communication for that can be done through that support. Okay, here's just a few actual code snippets that a caller would invoke to use the 2D version of this grid class. So if you want to define an instance of a global grid that's global size nx by ny, you instantiate, you have then a pointer to this class, and nx and ny are two arguments at the end here. There's then a handful of methods you can choose to decide if or how ghost cells are going to be defined for each processor. And then to partition the grid, you can actually return the extents for both the own cells and the grid cells. All these arguments are returns with this setup grid command. And so the ones that start with I are the inner cells, the own cells, and then the extent with O of the outer cells. These are indices into the global grid. That's the subset of the grid this processor owns for both own cells and grid cell and ghost cells. And then if you want to perform forward or reverse communication, there's a couple of setup calls, or I'm sorry, one setup call that gives you back some buffer sizes that the caller needs to allocate to do this communication. And then you make a forward communication call and a reverse. You pass in these buffers, tell it the number of values you're packing into the buffers and the data type that MPI is going to use for the messages. And then again, the caller provides the pack and unpack methods to actually put its grid data into those buffers. There's a read file and write file methods to write out from a parallel set of processors the grid data to a file or read it from a file, and remap methods that you invoke whenever load balancing occurs to trigger the communication needed to reassign grid cells. And the caller also provides a few little functions that are these grid data access methods, so other classes can query with the name of a data set, the name of a grid, and get the values that it needs. Okay, so here's quickly the current use of distributed grids within LAMMPS using these two classes that I talked about. So we've had case-based solvers for a long time, both P3M, which is a variant of particle mesh Ewald, and MSM, multi-level summation method, but we refactored them to use these new grid classes now. And so as I said, for P3M, it gathers charge, does FFTs on the grid, scatters forces through electric field. MSM actually uses a cascade of grid sizes, so it instantiates multiple multiple sizes of grids and does the communication on those internally. And then we have a couple of new pair styles, Amoeba and Hippo, which are polarized force fields from the Tinker code. Multiple terms within that force field do their own FFTs, so we can't really just do it once in a K-space external module, so we do it within the pair style. And so similar to P3M, it uses the grid class in these ways to do those different FFTs. Then there's a couple of fixed styles. One is a new one called fixed TTM/grid, which is very similar to the older one, fixed TTM, but that used a global grid so that each processor shared a copy of the entire grid. This new one is now using the distributed grid. And so it's this two temperature model for atoms and electron heat or electron temperature. And what's nice about this is now you can do an arbitrarily big system because this grid is not shared or duplicated across processors, but distributed. Fixed AV grid can be used to take either particles or grid cell data and average it in time within grid cells and across time. There did used to be, still is, a fixed AV chunk command, which allows chunks to be defined, which are regular grid cells. But similar to TTM, it was a global grid, not distributed. So you were limited in how big a grid you could use and still be efficient. In particular, for large grids, AV chunk would be inefficient in CPU and memory cost. But now fixed AV grid can use arbitrarily large grids because they're distributed. So compute styles, there's a compute property grid, which allows you to access an ID for each grid cell and its corner points if you want to put that in a dump file, for example. And then a new dump grid style that lets you on a per grid cell basis dump out different values that applications have defined that live on those grid with it for the data. And dump image, which allows you to color grid cells, and that's going to be shown to you in a movie I'm going to show in just a second, likewise for dump movie. And then Oviedo itself, Alex Stukowski, I talked to him about this new dump grid capability, and so Oviedo can now read these dump grid files, and you could visualize the grid on top of your particles, for example, within Oviedo. Okay, so here's the movie I want to show. This is a movie or a model, smooth particle hydrodynamics, which doesn't really use grids at all. It's just particles. And so I'll show you first a movie just of the particles. This is the initial load balancing of the system. You have this column of water here that's going to collapse under gravity, flow over these two dams and hit walls on the other side. So the particles are colored by their kinetic energy. You can see the ones that are moving fastest. And I'll just play it again quickly. You can see the water flowing over this little dam here and shooting up in the air. So now I'm going to show you the same system, but I'm going to color grid cells instead of particles. So we're using fix av grid just as a diagnostic in the code to bin up the particles, assign some value to each bin. And in this case, the grid cells are going to be colored by the particle count in the bin. And now we're just going to use the dump image we're not going to show the particles in this movie, although we could show them on top, but it kind of obscures the grid cells. I'm just going to show the same thing, and you can see dynamically where the particles are going because of the higher density in the grid cells that are more red. So if you compare the last frame of both of those movies, one for particles, both for grid cells, you can see they're the exact same simulation. The decomposition of processors is the same, but here's the particle representation, here's the grid cell representation. And so again, if you had 1 billion particles and you didn't want to simulate, you could use a high resolution grid and you would get a pretty good representation with much less data of that simulation. Okay, so my final slide, just where can you go for more details? From a user perspective, within the user guide, there's a how-to grid page in the how-to section. Kind of tells you the current commands that use distributed grids and lamps and how to access grid data, the syntax for that in input script commands. And then in the programmer's guide, there's a developer grid, kind of a how-to on this that's in section 4 of the programmer guide, and it gives you more details about how to write a new style which uses a distributed grid. And in particular, it goes through all the methods that these two classes provide and tells you their syntax and how to use them and what they mean. So that's my stopping point. Let's see, did we stick close to time?
Close enough.
Okay. All right, so we've got 10 or 15 minutes left and I'll open up Slack, but Axel, if you see any questions there, we can answer questions either about the 3 talks or if you have just general development questions like, could lamps have this feature or how would I go about this feature or something like that, you can feel free to ask those as well.
Yeah, I just fielded a couple questions about the GUI thing.
Okay.
Let's see if there's any questions.
Hey, Steve, I had a question about the fixav grid. So when should we use fixav chunk versus fixav grid if you have like a 3D?
Sure. So fixav chunk, as I said, it keeps effectively a global copy of the grid on every processor. And so the way it works when it runs, it's summing up particles mapping into those grid cells. Each processor may contribute to overlapping grid cells. And so at the end, it has to do an all reduce across the global grid in order to sum up the values. So that's what could be the bottleneck. If memory isn't a bottleneck for a huge grid, that could be a performance bottleneck. So if you run and it's slow and it seems to be taking a lot of time in I think what in output is the modify section, which includes category of time includes the fixes, then you can try the distributed grid. It should work essentially the same way, but it has much smaller communication costs.
Okay, thanks.
And memory footprint as well.
Uh-huh.
So if you really want to see a problem, run a big problem with 1,000 by 1,000 by 1,000 3D grid with fixav chunk, and you'll probably blow out memory. And even if you have a big memory machine, you'll probably grind to a halt in your time stepping.
Right. So there was another question in Slack. If you have processors already distributed across the global grid, does invocation of the distributed subgrids initiate a redistribution of the processors?
So I kind of think of it the other way around. You write some code, and in your code, you either choose to have a global grid, which goes across the processors. That's what fixed TTM does. Or you choose to use these distributed grids, in which case there is no global grid on all the processors. There's only a chunk on each processor. So think of the processors first and what they're storing. It's either a distributed grid or a copy of a global grid. And now that motivates whatever else the algorithm has to do. And so the distributed, when you say invoke the distributed subgrids, you're not going to have a global grid anymore. You're going to have a completely different kind of grid, if I understood the question.
Those, are you able to, like, how are the grids distributed? Like when you load balance, are they also updated?
So I see a processor or a question about a laptop with only 2 processors. Can I use the distributed grid? Yes. I mean, from the user perspective, you're not choosing whether to use a distributed grid or not. The command you're using either uses distributed grids, and if you only have a single processor, then the distributed grid will overlay the entire domain because your processor subdomain is the entire subdomain. It is the entire domain, and that will work just fine. So you can certainly run a distributed grid feature in LAMMPS like P3M or something else on a single processor. It works just fine. It's just as you scale up to more and more processors, it will become more efficient to use a command that has distributed grids as opposed to a global grid. But from a functionality point of view, they're the same. So fixed TTM or fixed TTM grid does the same thing, just one will run more efficiently as you run larger and larger problems on more processors. I'll say the real aim of my talk on the distributed grids, obviously from a user perspective, it gives you a little understanding on how to choose one variant of a command versus the other. But my hope is there's maybe some developers out there that want to write a new model that uses distributed grids like MPM or something else that LAMMPS doesn't currently do that could leverage these distributed grids to do something efficiently. We heard a couple examples of talks during the workshop, one by Paul Atzberger about user Selm, which has a background continuum grid, and another one, trying to remember who it was, Bowen Lee. I can't remember the methodology, but he had some models that looked like were co-using particles and grids. And so in all those cases, maybe these distributed grids would be useful in that context if they want to write that part of the grid part of the model in LAMMPS. Okay, here's a question from Jan about the Python interface. Let me read it. Oh, maybe I'll read it out loud. Question about the Python interface. Is it possible to provide support for ACE, ACE package.atoms.atom objects as input for atomistic structures for the Python library? The challenge is primarily converting to the LAMMPS triclinic cell and back, but as this transformation has to be applied to all properties, people tend to struggle with this conversion. Different frameworks like ACE or PyIron have these kinds of conversions, but I could see this functionality being added to the default wrapper of the Python library. Okay, that's a very good question. I don't know the details about how, I know what transformation you're talking about, but I don't know the details about how it's done in ACE or PyIron, but yeah, that would maybe be a good discussion to have. And Jan, you're so expert in Python, maybe you can look at the LAMMPS Python interface you're talking about and suggest if a function needs to be added, or maybe it needs to be an option on some function that exists and what code, where we would put the code to do that. But yeah, we can definitely discuss that. I don't know if this is what Jan is referring to, but LAMMPS has a kind of a restricted definition of a triclinic cell. That's not the totally general 3 edge vectors of a unit cell. That one of the edge vectors has to lie along the x-axis, the other one along the y-x plane, and then finally the z one. And so that's maybe the transformation Jan is talking about, where you're going from, maybe ACE has a more general representation of those 3 edge vectors, and you have to map back and forth continuously to get from one to the other. LAMMPS does its restricted version so that the parallelism of chopping up that triclinics box is more straightforward. Okay, here's another question about a bond friction potential. We would like to write one which turns, for example, harmonic bond into a damped harmonic bond. In terms of the physics, this is for coarse graining. To do that, we need to access not just bond lengths, but the time rate of change of the bond lengths. Is that information available to programmers in LAMMPS? Are bond lengths actually computed, or are the equations cast in terms of the position vectors of the atoms? What's the best way to get started? So I think what you're saying is you want to write a bond style which does these bond friction potentials, and you want each bond to have a history associated with it. So, and maybe that's stored as simple time rate of change or some set of values that represents the last few time steps or something like that. So that is similar to the granular peristyles in LAMMPS, when spherical particles interacting and rubbing against each other for some number of time steps. There's a history to that interaction, which is stored on a pairwise basis by a class in LAMMPS that's called fixed neighbor, because you can really think of it as a property per neighbor that needs to be stored and persisted. And so I could see the same thing for the bond classes, and there might actually, if Joel Klemmer's on, he wrote some bond styles for this bonded particle model, the BPM package that I'm remembering. There might be some history effects. So possibly there's also already a class that stores history on bonds, but if not, something like similar to what's done for the neighbor history class, I think could be used to do what you're talking about. So that was Fred Phelan. If you get back to me, send me an email, we can converse with Joel and figure out if there's something already there, or if he's very familiar with the neighbor class because he's used it for different granular kinds of models. So I think we could work with you on getting that functionality for a bond style to use. Another question by Vishnu Kurupath. Follow up, the user does not get to define the distributed grid and they override the global grid when invoked. So for classical LAMMPS code using the processor command and the fixed balance, how does LAMMPS handle the processor domain decomposition? Okay, so for the commands I listed, like fixav grid or fixttm grid, the user actually does get to define the grid. That's one of the arguments to the command. You say fixav grid, I want a 10 by 10 by 10 grid, or 100 by 100 by 100. So after that, it is distributed, but LAMMPS will just automatically handle when there's load balancing takes place or when processor domains change for whatever reason. So I think all the things maybe you're asking about are automated within the code, and it's because fixav grid and fixttm grid use these grid 2D and grid 3D classes, which provide all the functionality for what you're asking about. So if you were writing new code, you don't have to worry about that part of it because the class is provided. And as a user, you don't have to worry about it at all. You're just choosing to use a distributed grid of a certain size, and it should just work. Let's see, I think we were at the hour. There's another question I see here about time domain parallelization and par splice efficiency. I will answer that one offline because I don't want to, it's 9 o'clock by my clock, or on the hour by my clock. So I think we should stop and let people go to the next breakout, which is 2 sets of contributed talks. Stan, do you want to say finally?
Yeah, so I was going to make an announcement on the breakout sessions. So now we have 2 breakout sessions of contributed talks. If you stay in this Zoom meeting, you'll get session 1, but I'd encourage you to look at the talks and pick the ones that are interesting to you so that we get some people in session 2 as well. And then we'll have a lunch break, and then we'll have 3 breakouts, granular EMC, which is a Monte Carlo structure builder, and then user SELM that we heard about yesterday. And then another 2 breakouts, Open Chem and PyIron. And the links are, so again, if you just stay in this session, you'll get to the Contribute Talk breakout number 1, the granular and the Open Chem. There's another link for Contribute Talk breakout 2, EMC and PyIron. And then for the user SELM breakout, there's a 3rd Zoom link. These are in Slack, and I also sent out an email. So again, I encourage you to pick the talks that are interesting to you, and if necessary, switch over to this second Zoom link to see the second session.
Okay, thanks everybody for the developer session.
And Trung, we'll turn the tab over to you for the contributed talks.
Trung, I'm not able to hear you.
We can hear you, Nikolai. Maybe you should just get started.
Okay, let me start. I'll speak about predicting the shear viscosities of liquids using LAMMPS. This property is of practical interest because it's easy to measure, and that's why we can verify our force fields for different kinds of matter. First of all, I want to say that we participate in industrial fluid property simulation challenges. They are organized by these organizations, and they are interested in blind calculations when they measure some property of liquid or fluid, and then this experimental data is not published, and they're interested how different groups across the world can predict this property. And during last challenges, and the very last challenge is held this year, they're interested how lubricant properties, some model liquid, properties change with the pressure or with the addition of some different molecules. And here you can see the scheme of the bearing, and that's how the description of these changes looks like. For example, the 10th challenge and the 11th challenge. So they only, for example, provide you the pressures and the temperatures, and they're interested in the viscosities at these conditions for these compounds. And now I want to show you how to predict the viscosity, shear viscosity using LAMMPS. Also, this property is very interesting for multi-scale modeling of maybe gas and oil problems. So they require also diffusivity and thermal conductivity, and all these properties could be accurately computed by LAMMPS. So basically, the force field model that we use in our simulations defines the accuracy of our predictions. And so we need to choose the force field very accurately before running our simulations for different kinds of liquids. But the main problem for the viscosity predictions is that viscosity depends on the strain rate. And for lubricants and for many water solutions, the problem is that molecular dynamics simulations, they apply the strain rates that are very higher than the experimental strain rates and the strain rates that appear in applications. And that's why we need somehow to predict the viscosities at 0 or like Newton region, at 0 strain rate. And first of all, I want to show you how to calculate the viscosity using non-equilibrium methods like Müller-Plache method. So we create the flow in the unit cell using fixed viscosity within LAMMPS. And I can show you how the flow is established. And we can find the velocity profile and find the viscosity here. And if we plot the velocity profiles in our unit cell for different pressures, for example, we can estimate the strain rate and plot the viscosity dependence on the strain rate, and find that for each pressure there are some dependence of viscosity. So we need somehow to extrapolate these dependencies to the low strain rates. And that's the problem about non-equilibrium methods. There are another approach called Green-Kubo relation, and it allows you to calculate the viscosity at zero strain rate. So first of all, you need to calculate the off-diagonal components of pressure tensor. Then you need to calculate the autocorrelation functions of these non-diagonal elements. And after that, you take the integral of this autocorrelation function. And all these methods are already implemented in LAMMPS. And that's how, for the molecular liquid, such stress autocorrelation function looks like. It oscillates because we have bonds in our models. And if you try to integrate this stress autocorrelation function, you will find out that for different statistically independent trajectories, you will obtain different results. And you need to somehow take an average of this over these trajectories, and also extrapolate this integral to the infinite time limit. And also the group of Edward McGinn, led by Edward McGinn, they provide us such a technique called time decomposition method. They extrapolate this average integral by double exponential functions. And now I want to show you how these integrals look for much more statistics at different pressures. And if you apply such an extrapolation, you will find that this integral converges, and you can obtain the value of shear viscosity. And if you then plot the viscosity at lower strain rates from the Green-Kubo method, you will find that these two methods converge to each other, and that's why you can use time decomposition method and Green-Kubo method if you want to obtain viscosity at zero strain rate, but you need to run a lot of statistically independent trajectories, or you can plot the dependence of non-equilibrium points at different strain rates and then extrapolate the data. So both these techniques could be applied, but in our works, we prefer doing these calculations using Green-Kubo method. And now I want to show you some results which you can obtain using LAMMPS. And for example, our blindly predicted data for such branched alkane. So the dependence of viscosity on pressure. And you can see that our force field that we use, it's a compass force field. It predicts the viscosity up to 600 MPa. And then experimental data were published, and you can see that quite accurately we are able to predict the viscosity of branched alkanes. After that, we tried to simulate aromatic compounds, 1,1-diphenylethane. And here I want to show you 3 isotherms for this compound, 3 different temperatures studied, and you can see the viscosity dependence on pressure. And the available experimental data is shown by points of different color, and our results at this pressures shows that we can try to predict the viscosity dependence at higher pressures. And now you can see our predictions, and then the measured data by Scott Baer in 2019 shows that our blindly predicted results for this compound also match the experimental data at the higher temperature, but as the temperature decreases, it becomes more difficult to predict the viscosity correctly, but we can predict the way how it grows, the law of the growth. Then we studied how to predict the viscosities of mixtures. And you can see that, for example, for such a mixture of aromatic compound and cyclic alkane, we also able to predict the viscosities at different molar fractions. And here, for example, stars are the experimental data, and the open circles are our results. And we can see that the inflection point of the viscosity dependence here appears for high 1-methyl naphthalene fractions, but as the concentration of naphthalene decreases, there are the inflection point of this dependence. Also, we apply these methods to predict the viscosities of water solutions, like 1,4-dioxane aqueous solution, and there is a problem to parameterize the interactions of this model, so we tried different force fields. And for example, for sucrose solutions, the accuracy of our simulations is much higher. For example, here you can see the black points. They represent the experimental data, and red points are our results. And also we are able to predict the viscosities of alloys using DeepMD potentials, like with ab initio level of accuracy. You can see here the dependence, concentration dependent. Yeah, Frank, thank you.
Nikolai, you have 2 minutes.
Yeah, thank you. So it brings me to the conclusions of my talk. So you can use both equilibrium and non-equilibrium methods, and all of them are available in this path of LAMMPS repository. So you can try for the Lennard-Jones system, and this workflow predicts the viscosities for the various liquids, but it should be verified. So that's all. Thank you.
Thank you for the talk. It's a very nice one. Any questions for Nikolai? So I have quick questions. Do you have, let me see if anyone asking about your talk in the chat.
Maybe in Slack, there are some questions.
Yes, so does anyone know that using non-periodic boundary conditions like FFS, how to control the pressure during equilibrium, and how to extract the correct stress and strain during compressions? I guess it is for your talk. It's not. Do you have any insights on that questions?
Yeah, first of all, I want to say that we use periodic boundary conditions for the non-equilibrium simulations. And if I understand correctly, how to control this. So yeah, when you do reverse non-equilibrium molecular dynamics, you need to somehow run a few simulations and have a look on the velocity profiles, and then you will estimate the strain rate. So it's better to just run the simulations and estimate the strain rate.
Thank you, Nikolai. I think we need to move on to the next speaker.
Yeah, thank you.
Let's follow up with questions after these sessions. So the next contributor talk with Rasul.
Thank you, Frank. Can I share my screen?
Sure, please go ahead.
So everybody see my screen? my sound is okay. My talk will be about molecular dynamic simulations for thermal fluctuations and kinetic friction in nanoscale. In macroscale friction, kinetic friction is related to linearly to the normal load. In nanoscale, it's not the case, because if a nanoparticle moves along the surface, then there's no net force for that. And in another example, we see that if a nanoparticle moves along some graphene layers, then for more number of layers, the friction will be decreased. So there are some complications, and it's a good reason for more investigations. We can consider velocity dependence for a start, to see is it the same, is there some similarity with the microscopic body moving through a viscous fluid, or what? For simulations, we start from model setup, then potential data file, equilibration, and molecular dynamic, and then we will see the results. A good reference for molecular dynamic simulations is Frankel and Smith book. Then the LAMMPS have been in our center of studies for making data files and also simulations. Also, we used VMD and OVITO for visualizations and data file production. In the model setup, in the left hand side, we see a spherical aluminum particle sliding in the x direction when applying a normal load and a horizontal force to the nanoparticle. There are some graphene layers. The bottom layers is frozen. So in the right hand side, we see the potential is complicated. We need force field for aluminium, carbon in layer, and carbon between layers. For the potential, we refer to a paper, physical review material, for interactions between aluminium and graphene in different scenarios. It's COM3 potentials developed by Professor Sinod from Pennsylvania State University. We communicated with them and concluded that this potential is good for our purpose. However, as we can see, this potential is time casting. It's expensive in comparison with machine learning potentials. It's here, it's empirical potential, but time casting like machine learning potentials. So we did simulations with COM3 potentials, charge optimized many-body potential. For data file, we started from lattice FCC. Then we made a spherical particle, melted and crystallized. The nanoparticle is made of about 32,000 aluminum atoms. And as the next step, we produced graphene layers with as an XYZ file in VMD, and then made it LAMMPS data file in OVITO. As for the next step, we have done simulations with box relaxation, and when applying a normal load, minimization, barostatin, to prepare for the molecular dynamic simulations. We also noticed that there is a range of forces. We cannot use every normal load. If normal load is huge, then the particle will smash the surface. We also noticed that sometimes graphene layers can move along the surface, and we need to fix the edges in just one direction. We use the same approach as Eric from University of California used for diamond impactor on graphene, and we fixed our edges like his approach. Finally, we have molecular dynamic simulations with tangential and normal force in 300 Kelvin. And the periodic boundary conditions applied in the X direction, and the upper, we have surface in the upper to see what is happening. The thermostat in Landrian is Landrian thermostat, and NVE time integration is applied. For the result, we see velocity dependence of kinetic friction coefficient, thermal dependency, normal load dependency, and then quantize the surface. The result is published or accepted in some journals. For velocity, we use Landrian dissipation model with random force. Then from simulations, we have a steady state regime for a fixed normal load and some horizontal forces. Then we see that in a few nanoseconds, the steady state regime will be reached. And from the theory also, the simulation time can be estimated. In our range of forces, we see that the linear dependence on velocity is a good approximation here. Although we know that the friction, kinetic friction, is the dependency of friction on the velocity is more complicated, but in the first approximation and in this range of a normal load and tangential force linear approximation, it works. Second, we investigated the thermal temperature dependence, and we see that we observe that as temperature increases, the friction coefficient will be decreased. It's non-trivial, and it's because thermal activation will help the nanoparticle to overcome the potential barrier easier in higher temperature. For normal load, we used fluctuation dissipation theorem and evaluated the friction coefficient. The friction coefficient is dependent on normal load squared, so also it's non-trivial, and properties of the surface. For graphene, we estimated the theory. The red dashed line is estimated in the theory for the graphene, and the points with error bars are simulations for two different temperatures, 1 Kelvin and 300 Kelvin. Because in Landrian thermostat there is noise, and in higher temperature there is also more the effect of thermal activation. After that, we thought that we can quantize the surface fluctuations we have quantum amplitude, quantum phase, quantum force, and then quantum time correlation function. The result is kinetic friction coefficient in the first approximation is the second Debye function, and in the in low temperatures we will have super slippery, and in a higher temperature we have asymptotic value of classical friction coefficient. This result is published, and for the next step we think that we can do quantum thermal bath using LAMMPS by QTP package, similar similar approaches already have done for thermal conductance and heat capacity, and published in PRL papers, and we have a good hope to do so for kinetic friction coefficient. Thank you for the opportunity from LAMMPS Workshop, also my supervisor and other colleagues.
Thank you so much, Rasul. Any questions from the audience? I'm trying to find anyone on the Slack. Thanks, Rasul. It's very nice contributions. And it's good to hear that you have been using a lot of features that LAMMPS provide for these studies. So we have 1 or 2 minutes left. I want to just, out of curiosity, so why quantum theories contribute to this length time scale? Can you, let's say, briefly explain to us for in a very short term time?
Yes, we try to quantize the surface. The surface amplitude is about angstrom. So we think we model the surface by a sinusoidal function, and then quantized it by quantum amplitude with annihilation and creation operators and phase operator. Then we averaged average is expectation value in quantum averaged, and use the average in the fluctuation dissipation theorem, and estimated the friction coefficient, kinetic friction coefficient. Then there are some studies in PRL published that with the same approach, quantum thermal bath, already simulated, and also in LAMMPS, I think with QTB package, we can do it as the next step. So the particle is still classical, but the surface is quantized.
Cool. Thanks for explaining. Cool. So we have,
if I just, because the particle is classical, there is no tunneling, for example. So it's clear.
Thanks, man. So next talk will be Daniel's. Please go ahead.
All right. Thank you. My name is Daniel Bikiel, and I'm going to talk about some work we've been doing. Let me go full screen. Some work we've been doing on ring polymers in LAMMPS, and looking at ring and linear blends. And so plastics are all around us. You probably have dozens of plastic materials sitting on your desk right now. And these kind of commodity plastics are made typically from linear hydrocarbon polymers. And so when we think about kind of the melt processing of plastics or polymer materials, we kind of have this mental image of a bowl of spaghetti, that these polymers are all tangled up, and they interact with each other and are kind of restricting each other's motion, and that's what gives some of the solid-like properties that we can see in plastics. There's a really interesting topological effect in polymers, though, which is if you change nothing about the chemistry, but just connect the ends of those two linear polymers, you get very different materials properties. And so on the right here is a sketch of just what linear polymers look like. And instead of being kind of spread out and interacting with a bunch of other polymers, they're instead much more compact and kind of these loopy, somewhat fractal looking objects that end up being, as a bulk material, much softer than linear polymers. And that's because you don't have this huge entanglement network. Instead, you just have a few kind of interactions between different polymers. So without changing chemistry, just changing the topology of molecules, we can get very different materials properties. One way to look at this is just thinking about the viscosity of linear polymers versus ring polymers. So that's what I'm plotting in this graph. We have viscosity on the y-axis, and on the x-axis, we have the volume fraction of rings. So we're actually going to think about blending these things too. But at 0 ring volume fraction, we have 100% linears. Whereas at 100% rings, it's a much lower viscosity. So as I said before, these are kind of much squishier, softer materials if you just have pure rings. What's interesting, though, is when you blend the two together, you end up with a much higher viscosity material than either of the individual components. And so this is somewhat surprising, but we can understand why by understanding a little bit about polymer motion. And so if you have just pure linear polymers, we think about those kind of entanglements and restricting the motion of a single chain. And so we're going to focus on this black chain here. And in traditional polymer physics, we think about this chain being confined to an effective tube, which you can see in this shaded region. And that tube is defined by all the other polymers that are nearby that are going to restrict where the black chain can go. And so the black chain has two ways of moving. It can move through this effective tube kind of in a snake-like motion, and we call that reptation. But the other way the black chain can move is these constraints can actually be released. So these small circles represent other polymer chains kind of coming out of the page towards us, and those polymers can move too. And so this shaded circle represents a constraint that was there at some earlier time, and that's when we had the shaded tube. But then that constraint gets released because of the motion of this other polymer, and then the whole tube can move. So we call that constraint release. And so we have these two mechanisms of reptation and constraint release in linear polymer melts. Now, when we blend together rings and linear polymers, we end up with linear chains that pass through the rings. So we call that a threading. And when you have this kind of constraints, there's no longer any constraint release because the ring can't break open. It's covalently bonded together. And so the only way to relax this sort of constraint is for the linear chain to reptate out from the ring. And so we lose a mechanism of, you can think about it as a mechanism of stress release or constraint release. And so we end up with a more viscous material when we have some rings in our melt of polymers. And so what we would really like to understand is this mechanism of linear and ring polymers threading and study the dynamics of that. And we're going to use LAMMPS to do that with some coarse grain simulations of just some Leonard-Jones beads with Feeney bonds to make our polymers. But to interrogate this kind of interaction, we're going to turn to some tools from topology. And so in topology, there's this idea of a linking number, which is really easily defined for closed curves. So if you have two rings, like on the left here, if they're not connected in any way, we assign that a linking number of 0. They're unlinked. Now, if one of the rings passes through another one so that you get kind of a chain link effect, we assign that a linking number of 1. So these are kind of clearly topologically different, and this linking number is what's known as a topological invariant. So you can change the positions, but the topology is kind of well-defined difference between these two. You can actually get linking numbers higher than 1. So if the two rings wrap around each other in a more complicated way, you can have a linking number of 2 or 3 or any integer, actually. And so one way to compute this linking number is just from inspecting these diagrams and counting the number of crossings and dividing by 2. So in this one, we have 2 crossings, so it's a linking number of 1. And you can kind of repeat this exercise. These crossings are actually signed, so there's some more complication to that. But that is one kind of topological approach. There's actually an alternative way to compute the linking number, which is via an integral. And so I've shown here this double integral, which is over the curves that define these 2 rings. And so this is known as Gauss's linking integral. And you can show that it will produce the correct linking number for these different chain configurations. We can evaluate this integral numerically if we have ring polymers that are have some defined by some beads in a simulation. So this integral is going to be useful to us. Another nice property of this integral is that we can generalize it to not just closed chains, but open chains or linear chains as well. And so what we're going to do is we're going to take our system of ring and linear polymers and apply this integral to pairs of them to figure out, is a linear chain threading a ring or not, and then evaluate some of these properties of ring linear threads. And so I've sketched here a couple configurations of a linear polymer in red and a ring in black. And so if the linear chain passes outside of the ring, but is close by, you'll get a value of this Gauss linking integral of around 0.1, so kind of close to 0. I should say that when you have open curves or linear chains, this integral no longer gives just integer values. It gives all possible rational values. And so if, in contrast, we have a linear chain that actually passes through the ring, we get a value that's much closer to 1, not exactly, but we can kind of tell just from this value of output by the integral whether 2 chains are linked. And as you kind of get more complicated wrappings of this linear chain around the ring, you get higher values of Gauss's linking integral, which I'm going to start calling the GLI. And so a collaborator of ours, Eleni Panagiotou, actually implemented this calculation outside of LAMMPS as a separate software called TEP, which is open source and freely available. And so that's what we've been using. And so at the top of the day, Steve talked about kind of, is it better to implement things in LAMMPS or outside of LAMMPS? And in this case, implementing this as a pre or post processing feature ended up being the right strategy for us. And so our workflow is we simulate things in LAMMPS and then evaluate our dumps with a separate set of software. And so I'll show an example of how we can use this linking integral to look at actual materials properties. And so some collaborators of ours, Professor Tingyi and his student Andrew, have been simulating interfaces of 2 different polymers. So this sort of thing will happen a lot when you have recycled polymers. So if you think about your recycling bin, you throw all sorts of different plastics in there, and there's a bunch of different types of polymers that are going in there. And when they get recycled, they end up being melt processed and then cooled back down into materials again. And so when you have this mixture in a melt and then you cool it down, things typically want to try and phase separate. The red polymer wants to be near the red polymer and the blue polymer wants to be near the blue polymer. So you end up with all these tiny domains with a lot of interfaces between them. And those interfaces end up making the material really brittle. The 2 polymers don't want to stick to each other. And so when you are applying stresses to a sample that's been made from recycled polymers, these are kind of the failure points that are going to make that material more brittle compared to sort of pre-recycled polymers. And so we'd like to be able to strengthen these interfaces. And so a strategy that our collaborators have been working on is using ring polymers at these interfaces. And so in the top part of our box, we have red linear polymers, and in the bottom part, we have these blue linear polymers. And then they're just adding a small amount of these rings that are half red and half blue. And so these rings are going to sit at the interface, and the hope is that the red chains are going to thread through, and the blue chains are also going to thread through. And that'll give you some constraints that'll hold these 2 domains together and prevent failure at that interface. So these ring polymers are kind of going to act like staples and staple that interface together. And so our collaborators built these things and equilibrated them and then sheared them. And On the right here, we have some data. So in the upper panel, we have the shear stress versus strain. So as we strain this sample, what happens? And so the red curve shows us the response when we don't have any rings at the interface. And the system fails reasonably quickly. So at a strain of around 1, the red curve hits a peak in the stress, and then it releases all that stress, or the stress goes down. And that's essentially an indication of the two domains slipping past each other at that interface, which you can see from visualization. When we add a small amount of rings to the system, we get this black curve. And so the strain at failure is about double what we had before, and we end up with a much tougher material. So seemingly the rings are doing something. They're helping improve the material's properties because we have ended up with this much tougher material. And what we can do with this linking integral is actually look at what are the rings doing. Are they actually doing what we think, which is in, threading with these linears? And so what this bottom figure shows is the fraction of rings that are threaded by both a red chain and a blue chain. So we're going to call those linking rings because they help link together those two domains. And initially we see that about 80% of those rings are linking the two surfaces. So they're doing what we expect of kind of holding the two things together. And as we strain the system, it goes down perhaps a little bit. I would say what's happening is basically noise. And then when we get failure of the material, that actually corresponds to dethreading of the linears from the rings. And so it seems that these materials properties are correlated with what's actually happening with the rings. And so we're doing further studies looking at how does changing the shape or the size of the rings and the number of rings affect the materials properties, and can we get sort of more significant strengthening of materials. So that's just kind of one example of things we can do by using these topological quantities like the linking number. I will say that this software that we've been using as an external package is parallel and reasonably efficient, but it evaluates all pairs of chains. And so we end up having an n squared cost, where n is the number of beads in the system, to evaluate these things. And one thing we've been thinking about is trying to exploit some of the more locality of LAMMPS, things like neighbor lists, to try and cut down on the amount of stuff we're computing. So we're not computing a bunch of zeros for two chains that are super far apart in the box. And so that's kind of a future direction of this project, and perhaps another integration with LAMMPS. So thank you all for your attention, and I will stop there.
Thank you, Daniel. Nice one. Yes, Nikolai.
Can I ask? Yeah, Daniel, thank you for the very interesting talk. I've got a question. So the results on the viscosities are your results, or you present some paper results?
So these are from the very first slide. That this is literature data. The black points are actually experiments. So I'm not an experimentalist, but I assume it was some polymers in a rheometer. The red points are other simulations from about 10 years ago. And I do not recall offhand how they computed viscosity, whether it was from Green Kubo or from
because like to simulate such systems, it's very difficult to do sampling in the right way, because it's very viscous, yeah, and you need to wait for long times.
Correct.
And you need to do sampling very accurately.
Right.
And that's an interesting question about this data.
Yeah, so I kind of skipped a lot of the details about the actual MD simulations, but these are big boxes. So typically 500,000 to 1 million Leonard-Jones beads, and they're typically simulated for 1 to 10 billion time steps. So you have to wait a really long time to both get good statistics and actually watch these relaxation processes happen. So yes.
And last question, how do you generate samples for your simulations?
Another great question. So yeah, rings are really tricky because if you're not careful, they will end up linking with each other actually, which changes the materials properties. So I did not prepare these samples, but I can put you in touch with a collaborator who did do that if you're further interested.
I'm sorry, we have to move on to the next talk at this time. Thank you very much again. Yes, let's follow up after these sessions. Next talk will be John's
Good morning, and thank you for coming. Today I'm going to be talking about elongational flow effects on ring polymers with associating groups. So the big sort of fundamental reason for doing this is that polymers are often processed in industry under flow, whether that be intentional or not. You can think of even like a solution or a melt going through a pipette or going through a machine that'll experience flow. And what we want to learn is how the chain topology affects the physical properties of these materials. And so ring polymers are particularly interesting, as we just heard, because they lack a chain end. So they're going to behave very differently from linear polymers. So here you have sort of a cartoon of a ring and a linear, and then this is what happens after flows is what we want to study. So the question is, we want to understand the effects of this flow with associating groups. So what happens if pieces of this polymer are attracted to each other? And that's really the goal of the study. So I'm not going to talk too much on the slide because it was kind of just covered a little bit. But linear polymers here at the top have an RG of about n to the 1/2, and the entangled linear chains will rotate as their motion, and they move more like a snake. And then if you have a ring polymer, the radius of gyration is a little smaller, n to the 1/3, and rings move more like an amoeba, and they have a loopy globular shape. So we want to understand how flow affects those ring polymers. And to do that, first was an experiment of ring polystyrene. So this is a viscosity plot versus time. And what we found was that there is a linear viscoelastic regimes that no matter how fast you flow the polymer, is going to have the same viscosity. And then there's a sudden increase of viscosity and then a steady state. And what was done was computer simulations of the same, or of a similar system. This is a bead spring system, and they found the same trend where you have a linear viscoelastic regime and then a sudden jump. And so the question is, where does this jump come from? And that comes from assembled rings that form daisy chains under flow. So this is kind of an image of these beads that are linked together. This is a close-up of that, where under flow they get linked and get knotted up, and then the longer chains essentially lead to a larger increase in viscosity. Okay, so to understand these questions, I'm going to be using about 1,600 bead spring rings, 400 beads per chain, and it's going to be using the standard Lennard-Jones potential from LAMMPS, using SLOD to calculate the flow. And so what we use is a mixture of non-associating beads where the interaction parameter between the blue is 1, and the interaction parameter between red and red varies between 1 and 8. So we can look at how the interaction will be affected by flow. And there's about 5% association level in these systems. So this is what a system might look like. You have a big simulation box, and everything that's in red is the associated groups. And so what we first did is looking at it as a quiescent study. And what we found is, as you simulate, because of the strength of the interaction, alpha 8 is much stronger, and it moves much less than alpha 2 or even alpha 1. And so if you want to quantify this, we look at the mean square displacement of this movement. And what we see is at higher alpha, at higher association strength, the diffusion decreases by several orders of magnitude. So increasing this interaction parameter greatly reduces chain mobility. And so next, I want to briefly discuss clustering of these systems. So a cluster is basically a grouping of those associated groups, and it's defined by a certain radius, a cutoff radius. And what we find is that for a lower association strength, you have a lot more smaller clusters. So this essentially means that they don't cluster as much. And then for a higher association strength, they have bigger clusters due to that. So overlaying alpha 1, alpha 2, 4, and 8, you can see that there's a shift between the smaller clusters and the larger clusters. So cluster size increases with increasing association strength. And these are similar findings to what we find in linear polymers. So from here, the question is, how do these clusters and the associating groups, how are they affected by flow? And so what we did is we simulated this under flow, and this is what the simulation might look like, where over time you get longer and longer chains. This is a higher associating strength. Weisenberg number is really just a normalization of the extension rate. So what you see is, as these are different times of the simulation, and what you can see is it's interesting that the ring polymer actually loop around on itself because of these clusters, and then as you extend longer and longer, the clusters will break, forming much longer chains. But what we really want to focus on is the topological constraints of these ring polymers. So that count outing that you saw earlier, how does that occur? How many count outs do you have? How's that affected by associating groups? And so what we can do, first looking at the viscosity of these things, this is alpha 1, where everything has the same interaction parameter. Again, you see this viscoelastic regime at the very beginning with a sudden jump, and then it will plateau. But if you look at a very high sticker strength or very high associating strength, what you see is almost no viscoelastic regime with a jump in viscosity and then a steady state after. And so what we can see is extensional viscosity for alpha 1 does follow the previous results, but for higher sticker strengths, there's a much steeper slope to this. If you actually take the final time step of these simulations and you just visualize chains based on size, based on length, what you can find is a much higher fraction of smaller chains for alpha 8 than for alpha 1. So these two images are all the chains that are size sigma equals 50 or below, and then this is 70, 120, and 200. And so for alpha 1, there's almost no chains that are very, very small. There's 6. There's few. For alpha 8, there's a much greater number, and this is due to the clustering that results in heterogeneous distribution of this chain length. So I want to quantify exactly how the cluster affects those cow knots and those topological constraints. And to do that, we use primitive path analysis. And so primitive path is the shortest distance between two endpoints of a chain into which its contour cannot be contracted without crossing any other chains. And that's it's a long way of saying we want to find the shortest distance between 2 points. And so essentially what you do is you take the end state of the simulation and you make the attractive potentials very, very high. So anything that is not topologically constrained will be reduced down to a point. Anything that is constrained with other chains will remain extended. And so this is the quiescent study from before. You can see that there's a lot of little tiny dots, and then there's very few topologically constrained rings, whereas after a pretty high strain with a associating strength of 8, there's a lot more chains that are constrained. So to quantify this, what you can do is you can just count up number of chains that are long, and this is what that looks like. So you have a fraction of chains knotted as a function of strain rate. And so plotted here for alpha 1 and 2, there is a peak here. But what we can see is that by increasing the association strength from 1 to 8, you reduce the number of knots in the ring. And this is most likely due to the chains clustering amongst themselves and not having as much mobility with a higher sticker strength. And so these are my conclusions. For elongational flow, what's interesting is that higher association, the viscosity increases much more rapidly with time. And by looking at that PPA analysis, if you increase association strength, you get fewer and fewer knotted rings from the study. So with that, I'd like to thank you and open up for questions.
Thank you, John. Any questions from the audience or anything on Slack? Quick questions. How long the chain that you are simulating in the bead
Along
spring?
the chains,
How
there's
long?
400 Leonard-Jones beads per chain.
Per chains. Okay, cool.
So the max distance that if you have a 400 ring, if you pull it all the way tight, the max distance realistically is about 200.
Mm,
Um,
cool.
Yeah.
And how many chains in a typical runs that you have been using?
So chains in a run, I've been using 1600 chains, and the whole simulation system is 640,000
Mhm.
particle speeds.
Cool. Thank you. So if there's no questions at this point, then let us thank the speakers again for the contributing very interesting talks. Yeah, so we can close the sessions at this point. Thank you all for sharing the interesting studies. And we can follow up with all discussions over Slack and any question that you can have. Thank you all.
Yeah, so this session will continue with breakout on granular and solid mechanics using LAMMPS at 12:50 Eastern. Just check out the website with the details of the other sessions. go. Dan, are you already here?
Yes, I am. Can you hear me okay?
You want to take over?
Sure. Actually, I'm thinking maybe Joel might start sharing. It doesn't matter. I could share it and I could flip for him.
How about you share and I'll start with the talking and then we'll swap over who shares midway.
Sounds good.
Since I think the intro is just like 1 or 2 slides.
Okay. 1 second.
Yeah, I mean, we've still got a few minutes until the official start.
Do we start at the hour or at 50?
Well, technically you started 2 minutes ago.
Oh, okay. Sorry about that. All right, so I guess thank you everyone for joining us again after lunch break. Apologies for the 2-minute gap there. I'm Joel Clemmer, and I'm at Sandia National Labs with Dan Balatananu, who's also co-presenting this this talk with me. We're going to be talking about some of the non-molecular dynamics features available in LAMMPS, in particular focusing on methods for modeling granular or solid materials, so larger length scale phenomenon. We're going to be talking about both the granular package, which has been around for quite a while, but has gotten quite a bit of updating in the past since the last workshop, so the past 2 years, and also a newer package called the BPM, or bonded particle model package. And Dan, if you want to switch to the next slide. So, I mean, what exactly is the idea here? So, as we've heard in many talks, you know, the bread and butter of LAMMPS really is molecular dynamics and really atomistic simulations. But there's no reason that LAMMPS is restricted to that limit. Of course, LAMMPS is quite general. It's generally just a particle-based simulation environment. So you can say a particle is a lot of different things. You know, a particle could represent a cell, it could represent a rock, it could represent a drop of water, or maybe even a planet if you go to astrophysical scales. There's really no sort of limitation. The main thing you have to do is you decide what your particles are, and you have to decide what kind of quantities are tracked by your particles. Typically, you know, in all these cases, particles always tend to have some kind of mass or density, but also like a velocity and position. But, you know, particles can also have rotational degrees of freedom, so they can rotate as if they're a finite grain. They can also have a finite shape or radius. They can have temperature and all sorts of other, you know, larger length scale quantities as well. Here's just sort of some demo illustrations of a variety of simulations that have been done before in LAMMPS. These are stolen from the LAMMPS website, where they model, you know, much larger length scales than anything atomistic. There is sort of a cellular scale, some model of blood flow. There's a scale that's supposed to represent more shear fault behavior. So something sort of on like tectonic scales possibly, or you know, the interface between tectonic plates. And then also sort of a dam break simulation using SPH. And in all these cases, you know, these are particles being simulated, and they have certain particular unique interactions that they have with their neighbors in order to model these different variety of behaviors. And of course, there are many different methods out there in the literature which capture different length scales. There's obviously MD, which is sort of the atomistic and molecular length scales. There's the discrete element method, which Dan will talk about in just a second, which captures sort of like grains or rocks, although the size of a rock is sort of up to you as well. There's a bunch of different methods for coarse grain, solid mechanics, peridynamics, BPM, and of course, a bunch for hydrodynamics, SPH and DPD. And so if we go to the next slide, what we'll see is sort of an outline of what we're going to cover sort of in this breakout. We'll probably keep it pretty informal. Whenever one of us isn't talking, the other will probably check the chat and, you know, feel free to ask questions, and maybe we'll interrupt and sort of provide some answers on the fly. Well, we'll first talk about sort of the discrete element modeling, so the granular package in LAMMPS. Dan will present sort of what models are available in LAMMPS, give a couple examples, and specifically talk about some of the new capabilities we added, which makes it a lot easier to add additional contact models. One thing about DEM, which Dan will talk about, is there's sort of a plethora of empirical and semi-empirical models that people have created, and it's easy to now add new ones to create new physics or new phenomena that you want to study. Then I'll talk about sort of the newer package, the bonded particle model package, which is more for, you know, solid elasticity and fracture. I'll show some example. I'll talk about the models we have implemented in LAMMPS currently, and give some examples from the LAMMPS directory, and talk through some of the complications of using the package. And finally, hopefully there's time, we'll talk about some other topics. You know, what are sort of some associated computes or fixes which are relevant, some of which have been very recently added to these packages, and also what other packages exist for different, you know, larger length scale dynamics that you might consider. At this point, I think I'll switch it over to Dan and let him dive into the meat of the granular package.
Thanks, Joel. So like Joel said, I'll talk about the granular package in LAMMPS, which is something that we work with quite a bit. So the idea of the granular package is to simulate sort of literal macroscopic particles where atoms represent discrete chunks of matter. Granular materials are everywhere. You can think sort of sand on beaches, powders in manufacturing, could be pharmaceuticals, could be 3D printing. Corn in silos is a popular application of these methods. And then a lot of the geomechanics world for things like rocks or soils in the Earth's crust. So again, like Joel said, the scales are really not, they span a pretty wide range from, micron-sized particles all the way up to sort of Earth scale, planetary scale even. The reason to simulate these kinds of materials using something like LAMMPS is that the behavior of these granular materials, whether it's powder flowing, has fundamentally different behavior that depends on the particulate nature of the material and the frictional contact between those particles. So continuum methods tend to miss a lot of that behavior, although there are some good continuum models for granular media. So we work a lot on simulations that try to get at both the fundamentals of granular physics and some of these applications. And there's a wide range of applications across sort of the industry, from, like I said, pharmaceutical to kind of earth moving equipment. A lot of neat ways to use these techniques. And I should say the title here, discrete element method, or DM, is the more common term that you hear in that literature. So I'll talk about DM and granular sort of interchangeably. I've got a table here just kind of contrasting traditional or molecular dynamics, which is probably what most folks are familiar with who use LAMMPS, with DM or granular simulations. So the atoms in MD are typically point particles, whether they're atoms or coarse-grained atoms, they have position, velocity, mass, whereas in DM, there's a notion of a finite size. And so atoms also have properties like radius and angular velocity associated with that finite extent and their rotation. The interactions in MD are typically long range, where the forces depend mostly on separation and they're conservative. Whereas in DM, we typically have only short range interactions, meaning when grains come into contact, and these interactions can be frictional and velocity dependent, which means they're inherently dissipative. The typical systems in MD are usually a representative sample, relatively simple boundaries, often periodic, but not always. And then the systems are often equilibrium, but again, not always. Whereas in DM, we often model full systems. So we could think about modeling, the entire bucket of this earth moving equipment, for instance. So the boundaries can be quite complex, both geometrically and in terms of their motions. And it's pretty much always a non-equilibrium simulation. A DM simulation equilibrium is just a pile of particles that sits there and does nothing. So non-equilibrium is kind of the default and more common case. All right, so what are some of the DM or granular relevant syntax here? Sorry, the animation here is a little off. So most of the key command is really in the peristyle. This is kind of the traditional form of one of the granular peristyles called Gran-Hertz history. I'll go through this one just really quickly, and then we'll switch over to kind of the newer syntax. Both are still available within the granular package. The idea is that there's a normal force between particles that depends on a very small overlap, which is kind of the definition of contact in these types of models. The normal force between particles is based on elasticity solution from Hertz from the 1800s, which basically has a stiffness here and a term that depends on the effective radius, which is a function of the radii of the two particles in contact, and then the delta here is the overlap to the 3/2. And there's also a viscoelastic term, and there's a few different models available for this, which has to do with dissipation or non-ideality of that particle collision. And this depends on the relative velocity of the two particles, which is a bit unusual for other peristyles and LAMMPS. There's also a tangential component to the force associated with that contact. And so that will induce forces on both particles, but also rotational torque. That tangential force, I've got the equation here, I won't go through it, but the key piece is that it depends on the history of that contact. And so as these particles sort of slide past each other, They accumulate a certain displacement that's tracked within LAMMPS as a vector quantity associated with that pairwise contact. This is something that's somewhat unique to the granular package, that we can have a history dependence of the interactions. And depending on that contact, you can then trigger slip criterion. This is a simple Coulomb friction model that depends on that accumulated displacement as well as the normal force. So that's kind of the simplest models. There's some more sophisticated options available. I talked about kind of the normal contact, which can be repulsive and cohesive. There's the sliding mode, which is the friction I talked about. Particles that are sort of in a relative rolling motion can also have torque associated with that rolling, so that they don't sort of slide or rotate past each other without any resistance, as well as a twisting mode where particles sort of rotate about an axis that connects their centers. For all of these different modes of relative motion, there's quite a few different models available. So the one I mentioned on the previous slide is the Hertz model for the normal mode. There's a few others. Hooke is an even simpler one. JKR and DMT are two that have a cohesive term, so that particles can support tension at contact that can be associated with van der Waals cohesion or more complex phenomena like capillary interactions due to the presence of liquid between those particles. Tangential modes, these are the different kinds of friction. I've just listed them here. I won't go through them. A couple of options for rolling and twisting, and then a new one that I'll got a slide on later on, which is a heat conduction. So these particles can actually, you can model the transport of heat through a granular medium with some new capabilities that Joel has added. So for JKR, which is one of these cohesive models, this is kind of the general form. Again, won't go through the equation. It's a little more sophisticated or more complex than the Hertz. And here's some details on the syntax. So the old syntax, which I had on the previous slide, it's the Gran-Hertz history peristyle. That's still in LAMMPS. People still use that quite a bit. So you would specify all the different coefficients, and the doc page for that peristyle has the meanings of these different coefficients, as well as the equation that is associated with that. In a peristyle like Gran-Hertz history, all the particles have to have the same interactions. The relatively new addition is kind of a more generalized peristyle, which is peristyle granular. That will be the focus for the next few slides, where you can specify, first of all these different options for different pieces of the contact model. So the first term is usually the type of normal contact model and its associated coefficients. And then you can specify tangential modes and all the different types of models that you can have for the tangential mode or the friction. You can also do things like specify a different damping model, and there's options for that. And you can specify different interactions for different types. So you can have, so one type of particle that's sticky and one that's not. And I've got a few examples of the kinds of simulations that can be run with that. This is a little different from the most LAMMPS peristyles in that the coefficients and some of these sort of keywords or model types are specified as part of the pair-coef command instead of the peristyle command. And that's all. There's quite a few examples on the doc page for a pair granular. All right, so a few examples here. This is a pouring simulation with 3 different particle types that have different cohesion between those types. So the red particles are very sticky. You can see they sort of form these almost like wet sand structures that can support themselves. Again, the box here is non-periodic. There's a flat wall on the bottom, and gravity is applied to the particles as they come into the box. There's a few ways to do this. Fixed pour is what we use a lot. This is something that insert particles into the box in a specified region. This is another somewhat more like an MD simulation in the sense that it's a periodic system with both cohesive and non-cohesive particles and a Langevin thermostat applied to them to introduce sort of random motion. And you can see after a while that the cohesive particles, which are red, will form this interconnected percolating network, whereas the blue particles still are relatively free, and that's due to the differences in cohesion between them. illustrating these rolling modes. So if you just have if you bounce a sphere along a surface without any sliding friction, it'll continue to slide and not rotate at all. In the traditional granular repair styles, you could have sliding friction, and so that would induce a torque on the particle as it impacts that surface, and then it will continue rolling. But it'll actually never stop rolling. In order to do that, you'll need a rolling friction term, and so that gives you kind of the more realistic behavior of a particle that impacts the surface. It gets torque as a result of the friction, and eventually stops rolling on that smooth surface. Let's see, a couple of other examples here. Getting into some more sophisticated simulations, a lot of the sort of periodic pressure and displacement controlled types of simulations that can be run in MD can also be run in the context of a DM or granular model. This is an example using combination of fixed deform and fixed NPH sphere, which is basically acts here as a pressure controller with the extra sphere suffix, meaning that it also integrates those rotational degrees of freedom associated with granular particles. This is work from Ishan Shrivastava, who was a postdoc here a few years ago, looking at jamming behavior under different shear conditions, and there's a fairly complex set of flow conditions that one can apply to a periodic system. On the top right here, this is an example that's in LAMMPS. Some of the videos are in the gallery. So using a fixed wall grain region, which is a wall that has granular interactions, so all the same kinds of models that are available that I talked about for particle-particle interactions are also available for particle-wall interactions. These boundaries can be formed with various region commands. So in this case, you can probably identify a cylinder and then two, is it box? No, I always forget this, brick, maybe. So you can actually build up complex geometries from a combination of regions, and then fixed wall grain region, we'll take those as input. I don't have the full syntax here because it gets a little bit long, but you specify both the interaction model and the geometry based on combinations of regions. The region command takes keywords like move and rotate, so you can have moving boundaries, and you can do some fairly complex things. In this case, pouring particles into this mixer, and the rotation of those brick regions can look like a mixer. This is a funnel using a region cone, I think it is, and cylinder combined to simulate pouring through a funnel. And again, you can imagine, industries are often interested in things like hopper design. What's the optimal angle for a given material that can be cohesive and clog these kinds of powder handling systems? So a lot of interest from industry in that kind of simulation. Another capability in LAMMPS using multiple atom-style sphere or spheres combined to build up a complex shape. This is the green surface there is just a STL or triangle mesh-based geometry that's been sort of filled with these clustered overlapping spheres. And you can imagine as you increase the number and decrease the size of those spheres, you can reproduce arbitrary geometries with fairly high fidelity. Those can be combined into sort of molecules, which can then be treated with fixed rigid as rigid bodies. And that's the way we often do complex particle shapes in the context of DM or granular simulation. So this is just a snapshot from a paper from Mike Salerno, who is also a postdoc here, who worked on the flow and packing of cuboidal particles that have these frictional interactions. And so you can do pretty complex shapes. The workflows for generating these are sort of a LAMMPS pre-processing step that's up to the user to define molecule files, which LAMMPS can then read in and either pour or pack in the way you would with molecules. All right, last thing I was going to talk about on the kind of user overview side is a new capability for heat transport. So this is a feature that was in a big part of code called Lights, which was a spin-off from LAMMPS that's still active, but I think Lights itself is no longer being developed. It's been commercialized. And that's to do heat transport within a granular medium. Again, something that's relevant industrially, a lot of chemical processing that involves heating powders, whether it's a chemical reactor, fluidized bed, that sort of thing. Drying of, corn, other agricultural products. And so the basic idea is that each particle can have a temperature that's assigned to it. This is not temperature in the sense of a thermalized system where, you have the velocity squared as the kinetic energy per particle, but it's just a per atom property that's a bulk macroscopic temperature associated with that particle. That's done with fixed property atom currently, and you just specify the temperature keyword as part of that. The peristyle granular that I mentioned earlier, in addition to all the different modes, the normal, tangential, rolling, etc., there's also an option for adding a heat model. There's a couple of simple ones in there currently. So for example, actually the one I've got on the left here is a slightly different one, but heat area. And this is a conductivity associated with that particular combination of types. So you can actually have different conductivities for different types of particles, and you could specify that as part of the Perico-F command. The physical basis of the transport model is on the left here. So there's a heat flow associated, anytime the particles are in contact, the heat flow is a function of the temperature difference between them, where heat flows obviously from hot to cold. The total heat flow into a particle is the sum of the heat flows between that particle and all its neighbors. This coefficient H up front here is a function of conductivity and contact radius. So depending on your contact model, you can imagine if the particles are pressed in tightly and the force is high, the contact area is larger, and so therefore you get a larger area through which heat can flow. So that comes into these heat flows. And then finally, there's sort of an overall heat balance for each particle, which is just shown here, and that's a change in temperature that depends on this heat flow, and then the heat capacity and density, heat capacity and mass of that particle. So the main piece, like I said, is the peristyle, but then there's also another fix that needs to be invoked, which does this integration. So it updates the temperature, again, this macroscopic temperature associated with each particle as a function of all the contacts and temperatures of the particles that surround it. So here's an example of what a simulation like that might look like. And this can all be done sort of simultaneously with particle dynamics, so they can be moving and flowing. In this case, they've sort of settled, and it's purely a heat conduction problem. So the top group of particles here is held at one temperature, and then there's a bottom group that's held at a different temperature, and you can see that fairly quickly you get the this is all in the granular examples that are part of LAMMPS. All right, so I'll show a couple of examples so you're getting into a little more detail on some of these. I'll spend a little more time on the first one and then kind of go quickly through the others. So this is adapted, slightly simplified from an example that's within LAMMPS that's in the granular directory, examples granular in pour flat wall. This is just pouring two types of particles on a flat wall. So kind of the upfront simulation settings here, fairly standard LAMMPS issue commands. The atom style is sphere, which has a per particle radius as well as angular velocity. The boundary conditions are going to be periodic in X and Y and fixed in Z. That's going to be where that wall goes. For pretty much all granular simulation, com modify vel yes is needed. That ensures that velocity is communicated to ghost atoms because these pair interactions have a velocity dependence, which is a little bit unusual for most peristyles. We create the box, fairly standard. Here's the peristyle command, like I said, a little bit long. So peristyle granular, Perico-F1 star means particles of type 1 interacting with any other particle, including itself, will be a JKR normal model. This is a sticky or cohesive model, and the parameters associated with that. I think it's stiffness, damping, Poisson's ratio, or sorry, modulus, damping, Poisson's ratio, and this is cohesive energy. So that's the degree of stickiness. This is all on the doc page. The tangential friction model specified here. Similarly, a few parameters associated with that, a rolling model and a twisting model. So that's, particles of type 1 are sticky, 2 to 2, which is going to be blue to blue in this video, are Hertz, which is a purely repulsive elastic potential. So those will not be sticky. Here's the sort of pore part. So we define 2 regions that are cylinders. The bottom of this is about 0. So these are going to be somewhere in the top of the box. And if you look in the early part of the video here, that's where the particles are inserted. And insertions happen at certain intervals. So we define these 2 regions, and those are inputs to this fixed pore, which has, again, I won't go into all the details, but the regions associated with that fixed pore are where particles get inserted. You can specify the diameters of particles and their densities. Going back a little bit, NV sphere is the standard integrator for granular. Again, it's very similar to fixed NV, except it also updates the rotational degrees of freedom of the particles. Gravity, which is obviously what's pulling particles downward. And then the last one is the fixed wall grain that I mentioned. In this case, it's not a grain region. I'll show one of those examples on the next slide. The interactions are, again, granular, and then the syntax follows exactly the same syntax as the peristyles. That means that all particles that are part of the fixed group have those interactions with that wall. In this case, the wall is a z-plane at 0, and then the null specified there's no corresponding z-plane at the top of the box. These are some of the outputs and data, again, pretty standard. In granular simulations, it's often not, a sin to lose particles. You might not care if they spill out of your box. So, thermal modify, lost, worn is a non-default thing that will not end a simulation if you lose a particle, lose an atom. Although it's good practice to make sure you're not if you're not expecting to. One other note, if you dump files in this particular format, ID type, radius, mass, XYZ, that makes it really easy to read directly into Oviedo. And so this is just an Oviedo rendered movie that can capture the per particle radius associated with these granular particles. All right, about 10 minutes here. So maybe less. I'm sorry, this goes into all the different details. This will probably be good references slides. I won't repeat that. Forgot I had all this here. All right, so a slightly more complex example. This is pouring into a rotating drum. Similar structure. This is kind of what we're shooting for. So there's a pouring that happens quickly, and then the drum is tumbling. I just want to mostly show the moving geometry capabilities here. So pretty similar setup, similar peristyle commands. System geometry here is kind of the key piece. So there's a region which is a cylinder. That's the main cylinder you see on the right there. That has a rotate keyword and an open too. So these are sort of unique pieces of this setup. The rotate keyword induces the rotation, which you can't see in the movie because it's a perfectly smooth geometry, but you'll have to trust me that this is rotating. So that specifies an axis of rotation, or sorry, I guess this is first entry is the angle of rotation followed by the center of the axis and the direction of the axis of rotation. The angle is specified as a variable, and you can see later on down here that that is a function of the number of steps. So this is something that's changing through the run, and so the rotation is changing throughout the run, which is what induces rotation of this region. There's also the open keyword, which is kind of probably a granular specific thing. So this allows the top of the drum to be open, which is where we pour those particles in the first part. Couple of other, so the insertion is the same as the previous case, and I guess I can go into the zoomed in view here. So you specify the insertion regions and then specify a fixed pore based on those. The the changing system geometry. So we basically redefine, we define a top wall after the pouring happens, and basically cap this drum before the rotation. So there's a couple of stages to this. And again, sorry to have to skip through it a little bit, running a little short on time here. All right, so in the last couple of minutes here, I'll just quickly spend a bit of time on how you develop new contact models. Like I mentioned, there's a lot of existing options and there's a lot of other ones in the literature. You can currently, all these different models that are in there can be combined in pretty much any arbitrary combination. So you can have a certain model for the normal force combined with any model for the damping, the tangential, twisting, rolling, and heat conduction. In the old approach, there was a lot of duplication of code. From the user perspective, this doesn't change anything in the script syntax, but if you're interested in developing, there was a previous approach where all these different combinations were basically different if statements within the paired granular code. This became pretty unwieldy as you got to a large number of models and large number of combinations. So the new approach, the different submodels, so things like hook, hertz, are broken into their own individual classes, and then a new model can just be a separate class and a separate set of files. And Joel's put together a really nice how to develop grand page. I didn't put a link on here, but you can find that on the how-to pages on how to develop a new contact model. So here's kind of an example of the old paired granular in I think it's in the latest stable release, in the August stable release. The new version looks very different. And so there are certain methods that are specific to each submodel. So this is an example showing the DMT case. So there's obviously a constructor that defines a few things, the number of coefficients, whether this is based on material properties or just coefficients that are not associated with the material property, like modulus, Poisson's ratio. Those are converted to sort of local coefficients instead of having to have the developer track, which index in the coefficients corresponds to which property. That's pretty handy. And then the main routine is really the calculate forces. So this returns the normal force in the case of a normal submodel, and that's nicely contained here in a separate method as opposed to being buried in a large group of if statements. So a quick example on how you might add one. For example, if you had a piecewise elastic model, like a coded particle, how much work would this really take? Answer is not that much. So you just need two files, one that is sort of the .h file associated with this new submodel. This would be a grand submod custom, let's say. Could be whatever name you want. In that header file, you could have this would be the definition that is the script, the LAMMPS script string that the user specifies, the name of the class, and then what type of submodel it is, so whether it's normal, tangential, rolling, etc. This follows a lot of the other syntax with the important difference that maps again the degree of penetration of the particles. You'd have different stiffnesses, and so something that's relatively complex like a piecewise model like that actually ends up being fairly simple. Sorry, going a little over here. Hand it back to Joel.
Cool, yeah. I'm going to take over the screen share. So
you want to take over the sharing as well?
Do you want to unshare, Dan? Okay. I'm going to take over screen sharing so I can control where the clicker and everything is. Let me jump to the slide. And so Dan just went over the granular package, and I'll talk about a related package called the BPM package. There are quite some similarities to them, and which I'll point out. This one's a bit newer, and it's a bit more aimed at, let me see if I can get a little pointer. Hopefully that's showing. So it's a bit more aimed at modeling elasticity. However, it's also more general than that. So the idea is basically, all right, so you could represent a grain using a single particle, a single atom in LAMMPS, like in the DEM package, or alternatively, you could represent a grain using a whole bunch of particles, assembled in some generic shape. Of course, this is more expensive, but the advantage of this approach is now you can take all these particles and connect them with, say, springs, and now you have an elastic grain that can deform, it could break, it could plastically flow, and all sorts of interesting phenomenon. So qualitatively, this is these kind of ideas go back decades. It's basically just a spring network model. But it's been allowing us to do a lot of very useful techniques because it's simplicity and stability. In particular, if you're familiar with traditional bonded interaction in LAMMPS, there are two main features of this particular package that make bonds unique. First is that bonds now have memory. So much like when you're doing the DEM model, you need to maintain history of your contact, like whether frictional forces have built up. You also need to maintain history of what this bond has been through in its life. You need to know, first of all, for example, what's its reference length? Maybe each bond has a different reference length because you want some well-defined zero stress state. You can also track what was its strain history, how far has it stretched, what direction it was initially oriented. And all these things come into play in the models I'll talk about in a bit. The other thing the BPM package can do is it can efficiently break bonds or create bonds. So you can model things like fracture or evolution of this bond topology in a much more efficient method than sort of the traditional approaches of breaking bonds and LAMMPS. In addition, these features aren't currently used by any of the bond models, but the mechanisms are there, the infrastructure is built. For those of you who are interested in developing in the bonded particle package, there also methods have been built such that bonds can communicate with neighbors, and you can also evolve the stored properties on bonds through time. So let's give some examples. Where might you use this? So one case, for example, you might use these kind of bonded particle models to study large elastic deformations. Here you have an elastic system. Traditionally you might want to do elasticity and finite element method. But when you have large deformations, this can cause entanglement of your mesh, and you can get all sorts of instabilities. But with these particle-based approaches, it's very, very fast and very efficient and very stable. So you can do these sort of problems. You can also do problems chock full of discontinuities. So for example, problems with fraction fragmentation. You can look at crack growth, crack nucleation, and percolation of cracks and coalescence of them to lead fragmentation. Problems like this are hard for FEM because it doesn't handle these discontinuities well, and you have to remesh the system. There are none of those penalties with this. You can also do sort of mixed modal problems where you have highly heterogeneous materials. So this is a granular composite, so hard grains connected by some plastic binder, and the bonds in that binder allow it to both fracture and plastically flow. So you can model sort of complex composites, which are also full of discontinuities. So these are some sort of examples of what you might use this kind of method for. Currently, we only have 2 models available in LAMMPS. However, we're hoping to put more and more in, and a lot of the tools are there, so you can build your own variations on these models. The 2 models are basically based on the 2 main schemas that exist in the literature. One type of bonded particle model, you say each of your particles are just represent nodes in like a lattice. So they don't rotate, they don't represent like a physical grid. You can optionally smooth force to get rid of a discontinuity. And this can work with pretty much any basic standard pair style in LAMMPS. There's also specifically a pair style made to mirror this called BPM spring. The other type of bonded particle model you see a lot in the literature is more complicated. It's based on the discrete element modeling, the discrete element method. So here particles have rotational degrees of freedom. This is probably what you'll see most in the literature. There's a bunch of different names for it. Cohesive beam model is one I see a lot. But here you can think of a bond more as like a beam. So in addition to applying elongational degrees of freedom, to constraining elongational degrees of freedom, it can also apply constraints on shear forces by applying shear forces, bending torques and twisting torques. So you sort of imagine this as like an actual physical beam that's connecting 2 particles and not only preventing them from stretching, but preventing all other physical modes of deformation that you'd have in sort of a larger length scale sense. And each of these modes can be independently tuned. And so this particular bond style is compatible with all the granular pair styles. So all the ones that Dan just talked about for DEM work with this sort of approach. So you could connect a bunch of DEM particles with some network of these bonds and represent some larger conglomerate behavior. Now, there's several ways to create BPM systems. Just like in regular LAMMPS, you could imagine using external tools to write a data file. You could create a molecule of a bonded particle object. This is, I'll talk about an example in just a bit, but this is really good if you're talking about a granular system. So your molecule could represent some grain. And of course, molecule files store the bond topology. The other thing you can use is you can use sort of the pre-built creation commands available in LAMMPS. Create atoms to create a bunch of atoms in some geometry, then create bonds to connect some network between them. The only reason I sort of mentioned creating these systems is because there's one caveat, and that's particularly the reference state. So in all these bonded particle models, all of these bonds remember that initial reference position. So they can say, all right, this is my equilibrium distance, this is my equilibrium orientation. And what happens is this reference state is saved right when LAMMPS reads a bond from a data file, or creates a bond from a create bonds command, or creates the molecule. Then the bond says, all right, I have no reference state, I'm going to create one, and saves it. If you read or write data files, this reference state will not be saved. The only way to have this reference state persist across different simulation runs is to use a restart file. So that's just a sort of important caveat. If you don't use a restart file, then all your stresses and forces will reset when you resume the simulation. Another sort of more tedious detail of this package is, of course, we're talking about bonds. And so you can have some overlap between bonds and pair interactions. And, depending on your model, maybe you want to have it the case that you censor the pair forces between the bonded interactions, or maybe you want the pair forces there. Of course, LAMMPS handles this through what some of you know as special bonds. There are special bond weights for 1-2 interactions, so bonds, 1-3 for angles and 1-4 for dihedrals. In particular, only the 1-2 is currently relevant for the BPM. And the BPM only has really two choices. One is you can set the weight to 0, which is basically saying pair forces have no effect between two particles if they're bonded. So if they suddenly squish together, they don't get an extra repulsive contact force. The other option is to set the weight to 1, which basically says, sorry, I just said that backwards. Oh, no, I said that right. The other option is to set the weight to 1, in which case pair forces will also be felt between bonded particles. Now, there's several options to do this, and there's some tricky, or not tricky, but there are some requirements on how you label the commands. For instance, if bonds break, the 1-2 Coulomb weight, which is not relevant for the BPM because it doesn't have Coulombic interactions, but it is relevant because it handles how the neighbor list builds, determines which pairs are included. So there are some complex complications. I recommend reading the special bond page and the how-to BPM page to get sort of details on that. This slide also serves as sort of a quick reference. However, the thing I'll note is that there are safety rails all up in the BPM package. And if you happen to put in the wrong combination, they'll just ding you and give you an error and tell you what you need to fix. But there is some consideration there. So now I'll sort of dive quickly into some example problems. The first one is, well, both of them are from the examples directory and that are included with the LAMMPS distributions. They're a little bit modified like Dan's previous demos to make them a little simpler. The first case is sort of a problem of using the BPM package to model sort of elastic or soft grains. So here is an example of pouring in these squishy elastic particles, which kind of look like, some kind of pasta that you're pouring in. And now not only can you model the friction between them, the cohesion, all the sort of typical granular interactions, but you can model that internal elasticity to model something with a much softer modulus relative to the forces you're applying. Here in particular, I just based these grains based on a lattice. There's no reason they have to be a lattice. The bonds, the one nice thing about all these bonds is they remember their initial distance between the two particles. So whatever their initial configuration is, that will be their equilibrium length. Unlike traditional bonds and LAMMPS, you don't have to specify that equilibrium length. But in this case, they were quite simple. And so I sort of broke this input script down into five blocks, which I'll just kind of step through. The slides hopefully will be up for reference, but I'll sort of just highlight sort of the key things that might come into play if you decide to use this package or test it out for yourself. Highlight some of the more idiosyncratic or different options that aren't always seen in LAMMPS. The first thing I'll point out is, so here I am using an atom style BPM sphere. This is a variation of the typical sphere atom style, which you use with the granular package. It's fully compatible with the granular package. It just has a couple extra quantities like bonds that you need. The other thing I'll point out is here's this very specific special bonds command that you'll need to specify for the BPM package. In this case, it's set up that pair forces don't occur between bonded particles. There's also some specific settings that you might need for the Newton setting, depending on whether or not bonds break. If bonds break, you need to have both processors know that it broke, so it needs to have Newton bond off. In this case, bonds won't break, but in the next example, bonds will break. So in this case, I also just threw Newton off. Again, this is sort of included in the doc pages for more information. And then like the granular style, you need to communicate velocity to neighbors. And there's also, because bonds can extend some unknown distance, you generally need to specify a larger communication cutoff. The package will, of course, estimate how far a bond can stretch, and it will warn you if you don't have a satisfactory cutoff. Let's see. So then here I'm using a molecule file to create these grains. So I create some region, some box, which I have to pour particles in. One thing to remember is if you're creating a box, you need to specify extra space to store bonds and specials. So that's documented in the create box command documentation page. Here I'm loading a molecule, which sort of is just this sort of, like I said, this sort of crystalline cylinder, a little rectangle, some kind of prism. And next I have the geometry of the system. So much like in Dan's case here, I specify some large cylinder, which will serve as a cylindrical wall, and some smaller cylinder up top, which is the location where particles are dropped in. Here is using a typical granular pair style. You could use any granular interaction. And here is the bond style. So this is the bond style I said with rotational degrees of freedom. So the bonds act like beams. And that means there's a lot of coefficients that come with it, because there's a lot of free modes that you could consider constraining. And particularly there are 4 stiffness coefficients, then there are 4 critical values, which I'll talk about in a second, and then 4 damping values. So each of these stiffnesses correspond to the elongational mode, the shear mode, the bending mode, and the twisting mode. So you can independently set all those. You know, if you had some expectation from linear elasticity of what the stiffnesses of a beam's mode could be, you could plug those in terms of the Young's modulus and the Poisson's ratio of the beam. The other thing is the damping modes independently will damp all those individual motions if they're relative in the particle. This is all done in an objective manner, so it obeys rotational and translational symmetry, so you don't have to worry about your particle tumbling and then the damping doing something funky, aphysical. And then I mentioned the 4 critical parameters. Here, bonds can break if this quantity ever exceeds a value of 1. So here is the magnitude of each of the forces or torques in those main modes, normalized by the critical values. So here I just pick critical values that are really high, so nothing will ever break. There are options in the package to specify bonds don't break, in which case if a bond ever happens to reach that limit, it'll let you know. Let's see, here's some fixes that have the walls, nothing too unique here. Only thing I'm going to really point out here is that here is using fixed deposit to drop a bunch of these molecule files. And then also similarly how granular package has its own integrator, this also has another integrator. Instead of NVE or NVE sphere, this is NVE BPM sphere. There's a couple other things that need to be integrated. In particular, for those who are interested, the DEM package doesn't need to know the orientation of a particle. It just needs to know its current angular velocities. But in this case, because we need to know where a bond is pointed, we need that orientation. So there's a little extra integration of quaternions. Next, here's some output. I'll highlight this compute in particular and bond atom, which was added in LAMMPS with the BPM package. Typically, you know how many bonds are in your system, but if things can break, that number can change and maybe you want to track it. In this case here, I use it as sort of a metric to make sure none of my forces are so high that a bond broke. So I calculate how many bonds each atom has and then I tally them up across the entire system and print it in the thermodynamic output. So I can see, oh shoot, this number's changing, something's breaking. Let me return to my model. And then there's a couple key takeaways, all the things I mentioned. Feel free to peruse this, but at the end, this sort of gives you a way to model aspherical grains in a manner different than the rigid package. One thing for consideration, if you're comparing this to the rigid package, is A, is elasticity. B, this also might handle this may or may be more or less efficient based on the size or the geometry of your grains. This case is fully parallelizable, where with rigid, you have to be a little concerned about whether your rigid grain is larger than the processor domain size. The next example I'll give is also adapted from the examples. Here is a simple fracture problem. It creates a plate and it just throws a ball at it and allows the bonds to break. I'll sort of highlight some of the more salient features. Here I have another special bonds command, but here I said exactly what not to do. I set Coulomb to 0.0. This is a temporary setting. In this case, when I create the system, I'll use the create atoms and the create bonds commands to demonstrate that. But create bonds specifically requires 0, 0. So this is set temporarily to this value, and later I'll replace it with what you actually need. Here's the system geometry. It's basically just creating a sphere and a plate filling with particles. The only thing I'll note is then I use displace atoms call. So one thing to keep in mind with bonded particle models is depending on how many bonds you have, how atoms are configured, you're going to get different elastic systems. If you have some disordered packing, your elasticity is going to be isotropic. If you have some crystalline packing, well, now suddenly you're probably going to have some anisotropic elasticity in your system, and cracks are going to preferentially grow along those crystalline planes. So there's a lot of work in the literature discussing sort of these effects, and I recommend looking at it if you're interested. But in this case here, we just sort of shift particles a little bit off lattice, just so things are a little less anisotropic looking. Next is the create bonds command. So this is where I mentioned I was using, so I created atoms, and the next I use the create bonds to connect all atoms with a sub-distance to each other. Here, you have to define a pair style first. You may have to increase the size of your neighborless distance by increasing the skin such that create bonds can see far enough. And it requires that certain special bonds configuration. And once when those are set, after creating bonds, I switch everything back to what I typically would want, a more typical skin distance, and back to the special bonds with the Coulomb 1-2 weight of 1.0. Again, if you forget to do this, LAMMPS will let you know. You won't start generating a bunch of unusable data. Here for the bond style, this is now instead of the rotational style, this is the spring style. So particles only have translational degrees of freedom, no rotation. This greatly simplifies the model. It's a lot cheaper to calculate, and also has a lot fewer coefficients. Now it just has a stiffness, a failure strain, and a damping strain. So it'll damp the relative normal velocity between two particles. The other thing I'll point out, I probably should have pointed out here, is that there's this extra command when you're making the bond style settings, and it's called store local. What this does is it's basically creating an internal fix. And this internal fix is basically just going to be something that aggregates data that you can later print out. And particularly the data this is going to aggregate information on when bonds break for post-processing. So the first argument here is going to be the name of the fix, which will refer to it if you have like a dump command, as you'll see in the subsequent slide. Here, I just called it break bond. There's a frequency of how often data is updated in it. So every 100 time steps, it'll purge its memory and refresh. So you got to access the data before 100 time steps are up or it's gone. And for each time a bond breaks, what it'll do is it'll save the time the bond broke, the IDs of the two atoms that broke, and also the position where that bond broke. And so here now I call it dump local command and feed it the values from this internal fixed break bond that was created. And what this will do is create just a dump file every 100 time steps, which will list which bonds broke in that time step. You know, if you're doing this at a high frequency though, maybe you don't want to be writing all of the header file to the hard drive every single 100 time steps, particularly if say no bonds broke during that time. Like if you have an elastic loading that only fails at the end, you're going to get a lot of information written before you get anything useful. So there's also a dump modify command header no, which might be useful, which basically just cuts out the header information. And then what this dump file will do is it'll just create a big table full of that data. Every line will be a different bond that broke, when it broke, and where it broke. And then you could feed that into Oviedo to create visualizations to identify where fracture occurred through time in the system. You could post-process it to extract cracks and to, find populations crack statistics and study those and all sorts of stuff. And so those are sort of the main key takeaways which I discussed. But in the interest of time, I will assume that the slides will be up and people can read them. And I'll go on to just touch on quickly on some other tools. We might not have time for questions. I don't know, Dan, are there any questions in Slack that look particularly interesting that we should discuss now? If not, I'll probably just dive into the new features and answer questions in Slack instead of verbally.
You want to go ahead?
Okay, I'll just go ahead. All right, the first thing I'll mention is there was a talk earlier today by Joe Monti, which sort of showed this tool since the last LAMMPS workshop. A new variety of neighborless construction was added here. It superseded, there was an old version called multi, this superseded it. Now this is the new version called multi. Basically, the problem is what happens when you have a very polydispersed system, a system with very large interaction distances and short interaction distances. You could imagine defining a size ratio lambda, which is the ratio of the maximum distance to the minimum distance. And if you use the default neighborless construction, the time to build a neighborless computationally scales as lambda to the 6th. So as you go to really high size ratios, this totally dominates your computational time. You can't simulate anything. This same scaling persisted with the old version of multi. And so this needed to be rectified. So there was work done by Tom Shire, Kevin Stratford, and Kevin Hanley at the University of Edinburgh, who created sort of a prototype, who developed a new method and implemented a prototype in LAMMPS, which cut down fundamentally the scaling to lambda cubed, which is sort of equivalent to what you'd expect the forces to cost. And we managed to put this into LAMMPS and fully integrate it. And now you can simulate arbitrarily large system size ratios. I think this simulation right here is 1,001. It ran in no time. And this is sort of a graph of the relative time it takes to build a neighborless versus computing forces in a system as a function of size ratio. In the old cases, this is a cubic relation. It becomes untenable very quickly. Here, there's no scaling issues. There's also options in LAMMPS for the granular package and specific to automatically bin continuous distributions of particles. So it's pretty easy to use. And I recommend checking that out if you ever have a highly polydispersed system and your computer is really struggling. There's a couple other miscellaneous features that have been added that are relevant. For example, the create atoms command Axel added a new mesh option, which is really cool because now you can input like a STL, like a, I guess maybe that's like a CAD file. I'm not quite sure, but it's a triangle mesh file, which basically you can load in, complex geometries and use that as a template for where to place atoms. So now you can create atom walls made out of particles, which can have very complex shapes really easily, which is nice and very relevant to sort of these more mesoscale applications where you might have some complex system geometry you want to model. Let's see, some of these have already been touched on. A lot of these are in the documentation added. I'll sort of highlight some of the more newer ones. There's a fabric tensor calculation for those who are familiar with that. It's a calculation that determines sort of the relative orientation of contact forces and lets you aggregate and determine whether forces are oriented. There's a new compute in there that'll do that for you. There's a compute in LAMMPS that'll identify rattlers, which is in a current pull request, hopefully will be in soon. Basically, it looks for undercoordinated particles that are just jiggling around in your granular packing, and you can automatically find those so you can create a group on them and say, apply extra damping to settle them down during an actual simulation run. There's a new fix, which can calculate non-affine displacements, so D2men for those of you who are familiar. And I'm working currently on adding some more fixed deform controls. So not only can you have strain control, but stress controls and do much more complex loading geometries, which are necessary in a lot of granular modeling. Lastly, I'll also just point out there's a lot of other packages in LAMMPS. LAMMPS is huge. A lot of people do a lot of really cool things. Just because we talked about the DEM or the BPM package, that doesn't mean it's necessarily the solution to your problems. I recommend checking out all these other packages as well if you have a particular issue and see maybe whether they're more well suited to your problem. And beyond these guys I listed here, there are many others. So with that, I think we're just about out of time. So I will stop there. Thank you.
Hey, Joel, can I ask a question?
Of course.
To Steve. It was a question about your pasta particles. Is there a BPM parameter that would adjust how flexible those little or bendable those little particles are? I'm hoping.
Yep, definitely. In particular, for that case, you can just adjust the stiffness of the bonds. And because this is a rotational, these are rotational particles with multiple modes of freedom, you could independently adjust, say, the elongational stiffness to the shear stiffness to, say, model different Poisson's ratios. So if you reduce all stiffnesses, you'll get a really floppy particle. If you increase stiffnesses, eventually you'll get something that's basically rigid. And you can do everything in between, all sorts of elasticity.
Okay, so if I hook that parameter to fix adapt to change it over time, I could model the cooking of pasta, you're saying, from.
Yeah. I don't know how you'd model the water, but maybe you can couple it to SPH. Oh, that's another package, Rio, which I talked about last workshop, which hopefully will be coming out soon. All right, so hopefully this is perfect for all your Italian cooking needs. With that, I will stop sharing.
Thanks. That was a fun breakout.
Ilya, do you want to take over?
Sure.
I mean, you got like 5 minutes before it officially starts.
Okay.
Yeah, I think there's a break and the next breakout is supposed to start at the top of the hour.
Okay.
I don't see Elad yet. Is he coming later or?
I'm not sure. Yeah, I don't know. I didn't hear from him.
Okay.
If anyone's already listening, I'm going to put a question in the Slack to see if anyone is listening that did not hear my talk on Tuesday or Elad's talk on Wednesday. So I can know to maybe give a little bit of an introduction. I'm going to put it in the tutorial channel. Okay, it's 1 o'clock. Shall we get started? Or 2 o'clock Eastern? All right, well, I don't know if anyone is proctoring the session, but I will get started then. So I'm going to give a tutorial on OpenCam consisting of 2 parts. I am going to give a tour of the website and the repository. And I'm also going to give a kind of a demo of some LAMMPS scripts and using OpenCam in LAMMPS. So for the hands-on portion of this tutorial, it might end up not being hands-on because mybinder.org, the public place that hosts these binders, has been wonky lately. Jan in the other parallel session is having a similar problem, but I encourage you to at least try. If you can't, that's okay. I will run. You can just look at my demo and then do these things later. at your own leisure. But it would be good to try to start this now. So if you go to, so there, you can either just go to the OpenKim website, like I showed on Tuesday, and click here, and that'll try to open it for you. Or there are some development features I'm going to show. So if you want to see those, then you can go to the OpenKim GitHub, go to OpenKim demo, and then switch to the type labels homonuclear branch, and then click on here. Because the binder is already overloaded, I'm not going to start this, but you can try either of those ways and just have it try to load in the background while I am talking about the website. And I also put 2 messages in the Slack, and in the tutorial section, I'm curious to see how many people will be able to open the binder, if any. So by the time we start the hands-on part, please react to the appropriate message, whether you were or were not able to open the binder. We have been going with this public version, and we were just waiting for something to go wrong to know that it's time to start thinking about hosting our own. So maybe this is the event that causes us to host our own binder hub. Okay, so let us continue with the presentation, and hopefully people are having their binder loaded in the background. Okay. So first I have a few slides about more technical details about Kim, or kind of more organizational kind of schema type things, because you'll be seeing a lot of these during the Kim demo, and I don't want your eyes to completely bounce off of all these things you'll be seeing. So every item in the Kim repository has a Kim ID like this, and most of them have a prefix that's kind of more human readable. And then they have this machine readable Kim ID at the end that designates the type of the item. I'll talk about the types of items in OpenKim, the unique number of the item, and its version. So for this case is the EAM potential from 1994 from Erker-Lassie atoms, the famous potential. And I'm going to be showing links to documentation about these things if you want to look at that in more detail. So now I'm going to talk about the types of content archived in OpenKim. First, I'm going to talk about models in some details. The 2 main types of models in OpenKim are portal models and simulator models. Portal models are self-contained programs that work with the Kim API with any compatible simulator. So they are independent of the simulator. They take in positions, species of the atoms, and whether or not they are ghost or padding atoms, and then output the energies and forces. So this is this schematic right here. This is intentionally limited because including more information, we decided made the API too complex. We did have more options in the past, but we removed those. What this means is that these portable models are essentially limited to pair potentials and many body potentials with a cutoff. So they can't do things like Ewald because they don't know anything about the periodic boundary conditions of your system. And they can't do things like explicit bonding topology, like bonds or angles, dihedrals, etc., because all they take is the coordinates. Often these models use a so-called model driver. This is the actual code that encapsulates the functional form of the model, and then the individual models are the parameters for that model driver. So for example, we have model drivers for EAM, meme, Tursoff, and many, many more. And we have many more coming soon that Alad talked about on Wednesday. The Quip model driver is literally the only reason it's not online yet is because I was busy preparing for this. It would have been online if this workshop wasn't happening. The second type of model in OpenKim is the simulator model. And a simulator model is specific to a simulator. And in fact, right now, we only have them for LAMMPS. We have many of them for LAMMPS, but we only have them for LAMMPS. And in short, it's an encapsulation of a set of commands and parameter files that are specific to that simulator. So for example, these two LAMMPS scripts are completely identical. Under the hood, they actually run the exact same commands. On top is the LAMMPS script without Kim. So to use this ReactFF potential with iron oxide, you run these commands to initialize your simulation. You do whatever you need to do to create your box and your atoms. And then you run these commands to set up the interactions, and then you run your simulation. And then you also need to supply 2 parameter files in this case to run the simulation. And with the Kim simulator model, all of these things are encapsulated in the model. So all you have to do is issue these 2 commands that I'll talk about in more detail later, and I've already talked about on Tuesday. And sorry, I was looking at Slack. And right, so these encapsulate these LAMMPS commands, and again, all the advantages of having them archived, having them uniform. Everyone that uses the Kim model uses these exact commands. And as far as syntax goes, this syntax for initializing a Kim model, creating your box and stuff, and then telling Kim which atom types to map to the LAMMPS atom types. So this basically indicates that the LAMMPS atom type number 1 is oxygen, LAMMPS atom type number 2 is iron. This syntax is universal. So you don't. This is more technical than you need to know to use Kim models. So this syntax is also the same syntax you would use for portal models for any Kim model. And another thing I wanted to point out, that not only can this run with LAMMPS, it can also run with other simulators that interface with LAMMPS. So the salient case here is that ASE, if you use ASE, then ASE also has a Kim interface and all that, and you can plug LAMMPS simulator models into that interface because ASE works with LAMMPS seamlessly. And the advantages of simulator models is that these can do anything that the simulator can do. So they don't have, they can know about periodic boundary conditions, and they can know about explicit bonding, for example. And another advantage is that these will automatically be accelerated through command line switches. So, you can pass, when you run LAMMPS, you can pass a command line switch that makes it automatically use the Kalkos pair style version of the pair style you're using. If it's available, the Kim simulator models will work with that as well. The Kim portal models, some of them are very fast, and they can use, some of them are coded to use GPUs and stuff, but that's a more specific thing. Of course, you can use domain decomposition with any Kim model, but if you are specific, if you need some very specific accelerated pair style, then if Kim has a simulator model for that, it'll work with the command line switch. Probably need to go a little faster here. Okay, the other types of OpenKim content are tests. So tests are they're programs that automatically pair with models to compute their predictions for material properties. And we have a specific framework and definitions for each material property, what format they should take, what fields they have, etc. And there's a link for that documentation here. And similar to models, similar to portable models, they often use a test driver so that, for example, there's one test driver, one executable for computing coefficient of thermal expansion, and then the individual tests plug the structure into it, like diamond or FCC and the species, so like diamond silicon or FCC aluminum, and those are individual tests, and they all use the same test driver. And then the final types of KIM content are reference data. So these are archived reference data, usually DFT, sometimes experimental, that is in the same format as the property instances that the tests report, so that they can be directly compared through the query interface. And then also verification checks, which Alad and I talked about. These just make sure that the model makes sense from the point of view of basic physics, like objectivity and numerical derivatives, and some coding things like memory leaks and thread safety. Okay, so now I'm going to go to the OpenKIM website and give a little tour of the website. So this is the front page. Your menu up here will look slightly different. And of course, you're welcome to follow along and ask questions in Slack. This will look a little different to you because you won't be logged in, but this is the main navigation. You can access help, browse content, and you'll have an option to log in or join. We encourage you to do that. We don't really send spam. Down here, there are examples, including the binder sandbox that I referenced. Stop this. Then you can go down to, there are many ways to browse content. One way is through this periodic table, and you can browse by content type. You can look at models and tests. There's a button here to contribute models. It's quite easy to contribute models. So now I'm going to go to, I'm going to click on an element. I'm going to click on aluminum, and that's going to take me to the browse page. There are multiple ways to categorize each type of content. On the left is a menu for the different types of content in KIM. There's a very nice multi-species selection. So for example, if I want aluminum titanium, I just keep typing here and I get all the models for aluminum titanium. If I click on one of these models, then I get taken to a model page. On the top right here, there's quick navigation to the different parts of the page. And this page is different for each type of KIM item, but they do have some commonality. So here is citation info for this model, and including the so-called deep citation. That's a machine learning algorithm that tries to determine, so this is a graph of citations, and the green means that the paper, we think the paper used the model, and blue means we think that the paper just referenced the model as a reference, as background information. And if you see, if you want to contribute to training this model, please click here, and you can tell us whether the model was used or not, and that'll help us improve the model. Okay. If you scroll down, you can see the model driver that this model uses. You can see the verification checks I talked about. So this model does very well on the verification checks. Looks like it's a little imperfect on the numerical derivatives compared to the forces are not exactly the numerical derivatives of the energy. But B is quite good. We have very stringent standards here. And these aren't, failing some of these things or getting a bad grade on them won't disqualify a model from being accepted. Then if you scroll down, we have visualizers for various computed properties. If you scroll down further, you have actual results for every single test that has been run on this model. And then if you go all the way down to the end, then you see the actual files that this model is made up of. So when you download and use an OpenCAM model, this is the source that the model is built from. And we don't want to gatekeep. If you just want to use the parameter file, it's right here. Most of the parameter formats we use are compatible with LAMMPS. Then now I want to move on to talking about tests a little bit. First, I want to just point you to the documentation. If you go to About, you have great documentation. You can look here, Introduction to KIM Tests, and read that in more detail. But I'm going to go to Browse again. I'm going to switch over to Tests. I am going to actually test drivers. So there, because there are many thousands of tests, so I'm going to look at a specific test driver. I'm going to pick the new equilibrium crystal structure test driver. This is the test driver that Elad briefly mentioned. This is the beginning of our new crystal genome framework, where I'm going to actually put up a little context here. So this is based on the AFlow crystal prototype framework. I don't have time to go into this now, but this is basically a symmetry reduced description that's kind of very convenient, that can be used to describe every single crystal. So for this crystal, for example, this is so this string indicates that the crystal has this symmetry, and that allows us to create many tests. Right now we've added I think 1,400 on a trial basis, and once this is all done, we're going to have over 40,000 tests for each property, because there are just that many possible materials that we can test on. So then this is the page for the test driver. As you can see, it's quite similar to the model page, has metadata up top. Then if you scroll down, you can see all the tests. First, I wanted to mention that you can see here the KIM properties that this test driver reports. And if you click, we'll get back to that in a second. If you scroll down, you can see all the tests that use this test driver. Again, there are so many of them, because these are all different heteronuclear crystal structures. So this is, titanium oxide in this particular crystal structure. And if you, let me find something with like aluminum. Yeah. So if you click on this test for aluminum, palladium, and some crystal structure, you get taken to the individual test page, and you can scroll down and look at right, because we just upversioned these. Let me look at the previous version. You can see all the models that this test has been run with. You can see, if you click on expand, these tables are also on the model pages that you might have noticed. If you click on expand, you can see a summary of the results. So this is obviously a low symmetry structure because it has so many free parameters. So this is what it relaxed to. And then you can click here to see if you want to see the actual files produced by the test. And we also benchmark, we also time every single test. If I have time, I'll get back to that later. So that's a page, that's a test page. I also wanted to look at, I said I would look at the properties. So this is, if you go to a test driver or a test and click on the properties it reports, then you go to the property definition, and you can see exactly the keys that are contained in this property. So this is, we thought, what is the necessary information to describe the material property of binding energy at 0 Kelvin, equilibrium, 0 pressure. And we have all the information that we think is required to define that. So this is helpful for querying, so you know what's actually contained in the property definition. And there is a, again, documentation about this. It's Kim Properties Framework is where I would go to learn more about that. Okay. Now some quick notes about querying Kim content. Again, go to documentation and you go to querying Kim content. There's some information here about the possible queries. There's also the Kim query. Oops. Hopefully I'm not jumping around too much. There's the Kim query Python package. Where is it? I can't find it, but yeah. So there's a Kim query Python package that can be installed through pip. There it is. Yeah, that can be installed through pip, and you can read documentation and details about this package here. And as I mentioned on Monday, this can also be used through LAMMPS. So there's also the LAMMPS documentation about how to query things directly from your LAMMPS script. You go to the Kim command documentation, you scroll down, and there will be documentation about that. In order to to play with the query, you can go to browse and go to query the OpenKim repository. And there are two options here. There's a more simple query for just querying for test results. There are some examples here that will give you results. I obviously can't go into great detail. So this is our database is Mongo, and the most general way to query it is to do a raw Mongo query. This is quite cumbersome, but very, very flexible. And you can do everything except for the raw query directly through LAMMPS. This needs to be done through Python or some other method. There are some good examples here. So for example, get all FCC aluminum lattice constants in the model at random. This pre-fills the fields for you. It gives you the results. And at the bottom, it gives you all the different ways that you can query the OpenKim repository directly. And just to finish up the website part of this session, I'll just give you kind of my strategy for querying. You find an example that's close to what you want to do. You make it as loose as possible. You set a low limit so that you don't get an insanely big query. And so, for example, if I wanted to do something similar to this and start working with it, I would delete this fields filtering, and I would redo the query, and then it would give me all the fields that could possibly be returned, and then I could narrow down from there. Read the Mongo documentation and use Google. Oh, sorry. So then now we're transitioning away from the website, more onto practical hands-on stuff for actually using Kim models. And I wanted to talk about some installation details. I'm going to go to there are different ways to navigate here. I'm going to go to About Kim API and going to go to Obtaining Kim Models. So this is going to give some installation options. So this is pretty important if you actually want to use OpenKim. So there are two packages. There's the Kim API, which is the actual API, the software necessary to get simulators to talk to OpenKim models. And there is the OpenKim models package, which contains a collection of models. Of course, the Kim API is a prerequisite for the OpenKim models package. And also the OpenKim models package is not updated super frequently. I think it was only, it was updated almost more than 2 years ago. But so it won't contain the latest models that are on OpenKim. But in most cases, if you have the Kim API installed, then you can very easily download and build models that are new on OpenKim, as I showed on Tuesday. So the options for installing the Kim API are, first of all, we have pre-built binaries for various flavors of Linux and Mac OS, it looks like. We also have a Conda package that we're very thankful for Jan Janssen to maintaining this. He's giving the other breakout talk. And so the only exception to what I said about being able to install new models is Conda right now. We're working on improving that, but right now, if you install OpenKim from Conda, you just get the models that are currently in the OpenKim models package, so you won't get models from the past couple of years. Then there are options for installing from source. So unless you do Conda, you need obviously sudo to install binaries. If you don't have that and you don't want to use Conda, you're on, for example, on a cluster, then you have to install from source. The first option is SPAC. I'm not an expert on SPAC, but it's a manager for source installations, from what I understand. And if you're lucky, you can basically just copy and paste these commands. And even if you're on a computational cluster, it'll just work and install the Kim API for you. And then you can install the models you need from source. The instructions to install models are at the bottom of this page. It's super simple. It's just a couple of commands, and I'll revisit this. And then finally, the most flexible way to install Kim is to actually compile it from the source. You can download the source, and there are various ways of configuring the installation. The default way to install it is pretty simple. So that's that. And then on the LAMMPS side, there's actually on the how to build LAMMPS page documentation, there's a subsection. If you go to the extra packages subsection of that, there's a subsection for Kim with details about how to get LAMMPS to talk to Kim. There's actually a really simple option where LAMMPS can download and build Kim for you. I just have one word of warning for this because we've gotten repeated support questions for this, is that if you have a Kim API pre-installed on your machine already and you're building LAMMPS, you want to, with this is all CMake, I'm not familiar with the traditional make, then you want to make sure that this download Kim option is off. Because if it is on, you will end up with 2 parallel installations of the Kim API, which is certainly something it's meant to do, but if you do it accidentally, it can get very confusing. You'll install models and then LAMMPS won't see them because you're looking for them in a different place. Yeah, Axel?
I just wanted to say, so this automatic download is mostly meant for testing.
Okay, all right. Yeah, I've personally never used it. I'm just familiar with many people asking, having trouble because they used it. So, okay, so then the recommendation is just don't use it. You install the Kim API using one of the other methods and then make sure.
Yeah, the problem is you don't have access. I mean, you have to find the tools to enable the Kim management. And of course, if you have a separate installation, then they will conflict and use different folders and just creates a mess.
Mm-hmm. Yeah. So okay. So then just don't use this. It's off by default, but for whatever reason, sometimes people have it on.
Yeah. Well, we can change it, but it's really, if you have an installation, you want to use that installation.
Mm-hmm. Yep. Okay. So then finally, I want to just go to the, I already showed the OpenKim GitHub. There's a number of utilities there that I don't have time to talk about now. There's Cliff, which is a fitting framework to fit interatomic potentials, whether they're physics-based or machine learning, and deploy them straight into Kim. There's KimPy, which is a direct Python API to the Kim API, so you can get forces and energies directly from a Kim model with Python. So that's it. That's where I'm going to end with on the website half of the presentation. I wanted to go into some in development features, but I don't have time. I'm going to go to the hands-on. So now is if you want to, you can react to my questions on in the tutorial section, whether or not you were able to start the binder at the beginning. Again, you can either go to it from the Kim homepage or from the Kim GitHub. If you go to it from the Kim homepage, click on it right here. I'm not going to click on it. Okay, so if you go back to the binder on your own time, this is what you will see. It's a Jupyter notebook. If you're unfamiliar with this is just IPython. Any cell is code. It has an exclamation point on in front of it. It's a shell command. So I'm going to. This is an environment that already has the Kim API installed and LAMMPS installed and properly configured to work together. So I'm going to give some LAMMPS examples. So to start off with, I'm going to install the models I'm going to use. So this has the Kim API installed, but not any models. So this is the command that you use to install any models, to automatically download, build, and install models from OpenKim once you have the Kim API installed. So while that's downloading and running, so this is actually going to the internet and downloading the models onto this virtual machine. I'm going to go to the LAMMPS example notebook right here. And all of these examples are just going to be simple bulk silicon simulations, and they're all going to be static calculations. The point of Kim is to provide you with a model to give you energies and forces from the atomic configuration. From there, you can run any kind of simulation you want. So I'm not going to run anything particularly interesting. I'm just going to do single point evaluations of the energy. So this is what this is a LAMMPS simulation without OpenKim. Pretty simple. So the user has to provide their own, has to specify the pair style and provide their own potential. Then if we can run this with Control Enter or by pressing this play button, and it gives us a result very quickly. And just to contextualize what we're doing, I've added a little bit of visualization here. This is the unit cell. The atoms outside the unit cell are repeated just for clarity, but just a simple silicon in a diamond configuration simulation. So let's see now if our model's installed. Yep, so all the models that we asked it to install have installed successfully. So besides getting the API, when you install the Kim API, you also get this Kim API collections management tool, which has several features such as installing and building models. And also one of the commands is to list the models that you have installed. And we can see here the new models that we installed. These down here are the models that are example models that come with the API regardless. So I just wanted to check this to make sure that the models that we want to use in the Kim simulations are indeed installed. So this is the same simulation with OpenKim. So we can compare these side by side. So as has been mentioned several times throughout the week, in order to use an OpenKim potential, the two commands are this kim init command and kim interactions command that are issued before and after defining your simulation box and atoms. So that's very minor differences between the two. And then if I run the simulation, then I can compare. Let's see if I can scroll to the energy. Collapse this cell as well. Yep, so negative 34.7, negative 34.7. There are some differences in the decimal points after that due to the differences in the implementation, in the actual code implementation of the Stillinger-Weber potential. But in OpenKim and in LAMMPS. And throughout this notebook, there are links to the documentation to the relevant command. So there's a link to the LAMMPS Kim command. It's here again, etc. So you can see here that there is a small but finite pressure in this simulation, and that's because when I set up these simulations, I just put in some reference value I found for the lattice constant of diamond silicon. And that's not exactly the lattice constant that the Stillinger-Weber potential we're using has at equilibrium. Oh, and sorry, before I move on to the lattice constant issue, I wanted to mention that Kim also prints citation information. Again, as we've mentioned a couple of times throughout the week, here is brief citation information, and then if you navigate to the LAMMPS log file, you actually get the full bib text. So you can just copy and paste this into your paper. All right, so let's get back to the lattice constant. So Kim provides it through LAMMPS, through the query API that I talked about, a way to get the lattice constant from on the new file is on the left here, to get the lattice constant directly from the internet, to query Kim for what is the equilibrium lattice constant of this potential in this structure. And we can save that to a LAMMPS variable, A0, and instead of setting our lattice constant to 5.43, we can set it to that LAMMPS variable, whatever Kim is. So then if we run this simulation with the query for the lattice constant, it's going to take a little bit longer because it's actually going to the internet and querying. And we can see that the pressure is nearly zero and the energy is slightly lower because it's closer to equilibrium. So now let's try to change the potential. Let's try to run this. So these are exactly the same input file, except I've changed the Stillinger-Weber potential to this ReXFF potential. If we run this, then we'll get an error because this potential does not support the units we asked for. So one of the, when you do the Kim initialization command, you ask for a set of units. And this model does not support them. The simulator model does not support them. And just as a note, what would happen if you were doing this natively in LAMMPS without Kim? You would, if the parameter file you're using has unit hints in the comments, it'll also raise an error. But worst case scenario, if the parameter file didn't provide its units, then LAMMPS has absolutely no way of knowing what units it's supposed to be using. So it'll happily run the calculation and give you the wrong answer. So most Kim portable models are capable of internal unit conversion, so they'll just happily run with whatever units you ask for. But even if you're using a model that is not capable of doing unit conversion internally, there is a way through the Kim command, through the unit conversion mode subcommand, and again, the documentation for that is linked here, to make your script agnostic to the type of potential you're using. And the way this is done is that when you, so let's look at the syntax here. So when you issue your Kim init command, you add this unit conversion mode argument, optional argument at the end, and I'm gonna run this so we can look at the log file. What it does is it defines several LAMMPS internal variables that allowed you to convert your units from let me just double check to make sure I'm saying this correctly. Yes, so these variables that Kim defines for you are from the units that you requested. So in this case, that would be from metal units to whatever the internal units that the model supports. So the way I use this is that instead of putting wherever I would be plugging a number into my simulation. So for example, I queried for the lattice constant in angstroms, which corresponds to metal units. For lattice constants, it's really not important because the only two commonly used types of units are metal and real, and they both use angstroms. But just in case, I multiply this by the variable that was defined by unit conversion mode. And this way I know that I'm converting this value to whatever the model expects internally. Same here with the mass. And then when it comes to the outputs that the model gives, you go the other way around. So here I defined LAMMPS variable that divides the PE thermal keyword by the energy conversion factor. So I'm going from whatever the model outputted to the units that I requested. And because this is now, because I made my own variable to do this, I have to also define a custom thermostyle to be able to output this. And LAMMPS technicalities that I also put the original internal version here because that makes sure it's calculated and that allows this variable to be calculated. So if we look at this output, then we can see that the original internal model value of 800 something got converted to a -36, which is about on the same order as what we got with Stillinger-Weber. Let's see, Stillinger-Weber got -34. Then we are in the correct units. So that's all I wanted to show for this part of the demo. So I'm guessing most people were not able to get into an instance of this binder, so I'm going to skip the exercise, but you can feel free to go back to it on your own time. So since I have about 15 minutes remaining, I am going to go back to I am going to show some of the in development features that we have that are not part of the main presentation. So first, I wanted to show just a quick example of this Kim recommendation system. So it's not deployed anywhere yet, but it's developed enough where we can show a demonstration of it. So this is a combination of several of natural language processing and some logic on. I'm not an expert on how this works, but some actual logic on the configurations to recommend an interatomic potential for an application. The way that we envision this working, for example, is that you would ask this is, a marketing way to describe this would be like chat Kim. So you would ask this model, this recommender system to, for example, you want to find out what are good models for low dimensional materials, such as silicene or nanotubes. When we're developing this, Alad put together this list of potentials that he thinks would be good for these applications. And so one of the mechanisms by which we can try to use machine learning to recommend a potential for these applications is to do a text retrieval model. So what this does is it looks at the context. So this is integrated with the citation metadata in Kim, and this goes through the citations, and it looks at the context that each of these models were used in the paper, and guesses if this will be if they will be a good model. And as you can see, it does pretty well. The top 4 models that it recommends are, in fact, all of the ones that Alad thought would be, Alad Tadmor, he's the PI of the project, would be good for this application. The second part of the model is the deep citation model, which looks at the graph of citations of how different papers cite each other, and based on that gives a recommendation. And here it does a little bit worse. It recommends some that aren't in the list, but this obviously is an exhaustive list. And then finally, there's a configuration model, and I don't want to misspeak about how this works. Alad talked about this on Wednesday, but basically it looks at the data in CollabFit, our sister project that archives DFT data, and it's I'm not sure. I don't want to misspeak anything, but basically, by evaluating the energy and forces of the potentials in OpenChem on these configurations, it will rank. It will give a third mechanism that is based on actual calculations for ranking these potentials. So this is obviously still in development, but based on a fusion of these different scores, we hope to have a recommender system that does a good job. Okay, so am I set to end at 1:50, or do I have 10 more minutes?
You have until the full hour.
Okay. All right. So then another in development feature I wanted to show off is the comparison tool. So that's on the website. So we don't have a public release yet, but it is online. It's at compare-dev.openchem.org. And so this is kind of the consumer reports type tool that Alad talked about on Wednesday that allows you to look at the trade-off between model accuracy and model performance for different models. So it has a nice search interface. So I'm going to look at some aluminum models. Let's see which ones I choose. So this Erkelesi Adams model, this model, and it's the search interface is very nice. You don't have to retype what you're searching for. And this Morse pair potential. And I click on compare, and then I choose an OpenChem property to compare these on. So this is one of the new crystal genome properties. And it's right now it's querying the OpenKIM repository to get some information about your choices. You can name this particular comparison. I'm going to call this FCC binding energy. And then I choose, I have some different choices for this particular property. So I'm going to look at face center cubic. I'm going to click add. And that's going to give me a comparison of the values of this of these models compared to reference data. Well, actually, let me take a look at this. Yeah, okay. So then I can keep adding more. So this is a table of the results that these models give. And then here is the reference data we have in OpenKIM for these same measurements or same material properties. And then I can add more properties through the same interface, but instead of that, I'm going to actually load a full example with these already loaded. So I can show you the kind of the actual consumer report style interface. It's taken a while to load. Okay, so it's loaded the 3 properties that we wanted to compare on. So bulk modulus, elastic constants, and binding energy. And binding energy also includes lattice parameters. And then if I click on this comparison and errors, it gives me that consumer report style table that I talked about. So the color coding is how big the error is compared to the average reference data we have. You can change the scale, the color scale here, so you can change what's colored green and yellow and red. And then we have this graph of computation time on the x-axis and the error function on the y-axis. So these 3 models, the EAM is very fast and has a pretty low average error. The meme has the lowest average error, but it's quite slow. And then the pair potential is not really good at anything. These are quite sensible results. We know that EAM is super fast. Meme's more accurate, but much slower. And then finally, you can assign custom cost functions. So if you don't care about certain potentials, if I don't care about the binding energy, which is reasonable, then I can that'll change my my graph. Okay, so I think that's all I wanted to talk about today. I have 5 minutes left. I don't have time to get into anything else. So I would encourage everyone to revisit this binder and play with it on your own. I guess another thing I can mention that this binder is actually the Docker image that is based on is the KIM developer platform. That's a whole separate thing. That's if you develop KIM content that is essentially an emulation of the OpenKIM computation pipeline. So you can run KIM tests and KIM verification checks on things locally that you're developing, or if you're developing a test, you can run that locally. So that's linked here, and there's a lot of documentation about how to use that. But I didn't have time to get into the model development or test development aspect of OpenKIM today. So that's all I have. If there's any questions, please ask them in the Slack or here. All right, well, if there's no questions, then I think we will we'll end. Thank you very much.
Thank you.
Okay, so thanks everybody for hanging out and staying until the very end. I'll now close the session. Hope to see you online somewhere, and if nothing else, in 2 years with the next event. Ciao.
Bye, everybody. Thanks for coming.